Hello there and welcome to Just About Earth, where curiosity settles in slowly and science drifts along at the pace of a quiet evening. Tonight we're wandering into a different kind of question, one that lives somewhere between imagination and possibility. It's the kind of thought that arrives when the world feels still and you start to wonder what would happen if everything we know had to begin again. Not in a frightening way, not in a dramatic rush, but in the gentle, careful way nature always seems to rebuild itself when left with no other choice. Tonight we're exploring what it might look like if Earth were rebuilt after a catastrophe, not as a prediction, not as a warning, but as a slow unfolding of how a planet learns to start over. Before we wander too far, I'd love to know where you're listening from tonight. Maybe you're tucked under blankets, maybe stretched out on the couch, maybe even sitting somewhere you've been meaning to leave but haven't quite convinced yourself to stand up yet. Wherever you are, I'd love to know what the moment feels like for you right now. If this kind of slow science keeps you company, if it helps you drift or unwind or simply breathe a little easier, feel free to like the video or subscribe. It helps this quiet corner of the internet reach others who enjoy drifting along with big questions at a soft pace. And with that, settle in as we take a slow step into a world beginning again. When you imagine Earth after a catastrophe, the usual images might be loud, chaotic, full of rapid change. But if the catastrophe has already passed, if we're focusing not on the falling apart but on the rebuilding, the picture becomes much quieter. The noise has already happened. What remains is the hush that follows, the long span where dust settles, oceans calm, and the air stops shaking from whatever force pushed the world to its edge. It's odd to think about Earth in a state like that, stripped down to its most basic elements, no longer shaped by our routines, our buildings, or our constant movement. Instead, it becomes an enormous canvas of stillness waiting for something to shift. In that kind of silence, the first thing that stands out is how empty everything feels. Not hopeless, just empty in a way that's unfamiliar to us. No engines, no voices, no electricity humming along in the background. Even the wind might feel different because it would be moving through a landscape that hasn't quite decided what it wants to become. What remains depends on what kind of catastrophe took place. Some events strip the surface but leave the deep layers intact. Others scorch everything but give the atmosphere a chance to recover. Some push life to the brink but leave tiny survivors tucked away in places we forget to imagine. Whichever scenario you picture, the important part for this story isn't the destruction. It's the blank space that follows and what begins to fill it. In that blankness, Earth isn't finished. It's waiting. That's because planets don't give up. They don't stop at endings even when they look final. They move on to whatever comes next with a kind of slow persistence that ignores human timescales. And so if Earth were ever pushed into a position where it needed to rebuild itself, the first steps wouldn't be dramatic. They'd be subtle. Heat would redistribute. Pressure inside the mantle would continue shifting. Volcanic vents deep in the ocean would keep releasing minerals and gases. Gravity would continue pulling the planet into balance. Even in silence, even in emptiness, there is always motion. Imagine standing somewhere on this quiet, rebuilding Earth. The ground might look barren or scorched or rearranged, but underneath it, chemical reactions are already happening. Minerals reacting with water, vents releasing new compounds, sunlight hitting patches of rock that haven't seen the sky in ages. Those small processes are the beginnings of the slow transformation ahead, not because they're dramatic, but because they chain together into something larger. Earth rarely rebuilds through single, massive events. It rebuilds through millions of tiny nudges. If the atmosphere has thinned, it would start to reform long before anything living returned. Volcanoes would release carbon dioxide, water vapor, and sulfur compounds. Some of these would reflect sunlight, cooling the planet. Others would trap heat, warming it. Over long stretches, these opposing forces would find an equilibrium. If the oceans were damaged or evaporated in parts, they would slowly return through condensation underground reservoirs, and the steady release of water from within Earth's crust. Nothing would happen quickly. Everything would unfold over spans of time that don't feel natural to us, but feel perfectly ordinary to a planet. You might think of rebuilding as something that requires intention, a decision made somewhere. But the fascinating part is that Earth doesn't need intention. It simply follows the rules of physics, chemistry, and geology. Those rules create order from disorder without needing a planner. Lava cools into rock. Rock breaks into sediment. Sediment shifts into new formations. Rain carves valleys. Wind smooths surfaces. Step by step, inch by inch, a world remakes itself. This quiet period after a catastrophe wouldn't be dramatic to watch, but it would be full of potential. The planet wouldn't look like the one we know. The continents might be in new positions depending on how violent the event was. Coastlines could be reshaped, mountains flattened or pushed higher, new volcanic islands forming in places where no land existed before. Earth's history is full of periods where continents drifted, collided, split apart and reorganized themselves. A catastrophe large enough to require rebuilding would simply accelerate change that was already bound to happen over millions of years. As the atmosphere stabilizes and the land settles, water becomes one of the central actors in the rebuilding of a world. Water chooses where rivers will go, how oceans return, which areas will flood and which will dry out. It's patient but relentless, flowing along the easiest path until it carves channels and basins that become part of the new landscape. If Earth lost some of its oceans, vapor from volcanic outgassing and icy comets could slowly replenish them. If Earth retained its oceans, they would shift, redistribute and find new depths based on the shape of the crust beneath them. And beneath all that, chemistry would continue working uninterrupted. Carbon cycling through rocks, nitrogen returning to the air, oxygen forming slowly through reactions between minerals and sunlight. Even without life, these processes happen on their own. They take longer, but they don't stop. They are the foundations that allow life to return eventually, even if life has been pushed far into the background. In the deepest parts of the ocean, where sunlight never reaches, hydrothermal vents would remain among the most likely places for the first signs of renewed life to appear. These vents, rich in minerals and energy, are some of the most resilient ecosystems on Earth. Life at these depths doesn't rely on sunlight or oxygen. It relies on chemical energy released from the planet itself. Even if the surface were uninhabitable, these deep communities could survive or re-emerge. The rebuilding would begin with microscopic organisms feeding off chemical gradients, slowly filling the oceans again one small step at a time. If the land were empty, the first returning agents of change might be simple molecules and minerals, forming the structures that life can cling to. Clay-rich areas, for example, are excellent at trapping organic compounds, giving them surfaces to react against. Those surfaces may have played a role in life's earliest beginnings, and could do so again. Temperature gradients near volcanic fields or geothermal pools could also drive chemical reactions that push simple molecules into more complex ones. All of this would be happening long before anything resembling familiar life returned. The rebuilding of a planet doesn't start with forests or oceans full of fish. It starts with the tiniest building blocks working quietly. It starts with chemistry sorting itself out, with water reshaping land, with heat rising through fractures in the crust. The early steps don't look like life at all. They look like stone, steam, and dark oceans. But they are the foundation that everything else depends on. As time stretches on, the planet would continue stabilizing. The sky would shift from hazy to clear. The ground would cool or warm depending on how much sunlight the atmosphere now traps. The rotation of Earth would remain the same unless the catastrophe altered its tilt or speed. But even those changes would eventually form new patterns of day and night, new climates, new rhythms the planet would settle into naturally. Seasons might feel different. Ice might spread farther or melt more quickly. Rainfall patterns could reorganize. But none of these shifts would stop the planet from continuing its gradual recovery. And even though these early phases feel distant from anything living, they matter because they dictate everything that comes next. The shape of the continents determines where ecosystems can grow. The composition of the atmosphere determines what organisms can breathe. The temperature range sets the limits for what kind of metabolism can succeed. Every small detail becomes part of the blueprint for a new version of Earth, one shaped by whatever catastrophe preceded it, but not defined by it. Somewhere in this long span of quiet recovery, Earth would finally reach a place where it's stable enough to carry the next steps of rebuilding. Not finished, just ready for the next slow layer of change. And the fascinating part is that by the time the planet reaches that stage, the surface might look surprisingly calm. You wouldn't immediately see the enormity of what has changed. You'd see rock formations settling, oceans finding their boundaries, skies clearing, and warmth returning in places where cold once held stillness. The planet would feel like it's beginning again, not in a dramatic burst, but in the same patient way it formed the first time. And from here, the rebuilding would continue not with a sudden leap, but with the same quiet persistence that brought us to this point. The next stages depend on how life returns, how ecosystems restart, and how a planet that has been wiped clean decides what to grow again. Every part of Earth's history tells us that life always finds a way, unless the environment is truly impossible. And even then, the planet reshapes itself until conditions improve. Life might return slowly, molecule by molecule, cell by cell, or it might return more quickly if survivors were able to hide in places protected from the catastrophe. When the world falls silent, it isn't the dramatic silence people imagine in movies or stories, where everything stops in a single echoing moment. It's a different kind of quiet, one that builds slowly as the last traces of motion fade from the landscape, and the planet releases whatever force it had been holding on to. The quiet after a catastrophe isn't empty in the way a vacuum is empty. It's quiet because the familiar patterns have paused. The tiny background noises that make a world feel alive have stepped back. No birds testing the morning, no insects stitching the air with their wings, no rustling of trees pushed by animals passing underneath. Even the wind behaves differently, because it isn't weaving itself through forests or reacting to heat rising from cities, or skimming across the surfaces of lakes and fields shaped by life. Instead, it moves without guidance, sliding across terrain that no longer answers it in the same way. This quiet spreads outward until it feels as though the planet is holding its breath. The stillness that follows a global catastrophe depends entirely on what came before it. Some events take place so quickly that the world seems to tilt in an instant, leaving behind a landscape that no longer matches what existed just moments earlier. Others unfold gradually, slow enough that life attempts to adapt, move, or hide, but overwhelming enough that eventually the pressure of change becomes too much. When the process is gradual, the silence feels heavier, as though the world had time to understand what was happening and still couldn't hold on to the threads that usually tie everything together. When the process is rapid, the silence feels stunned, as if everything stopped mid-motion. In both cases, the aftermath carries the same weight. The world feels paused in a position it never meant to hold. If you could stand there in that silence, it would feel almost unreal. Not because the environment would be unfamiliar, but because it would be missing the tiny pieces your mind is trained to expect. Your ears are used to sorting through layers of sound. They pick out voices, engines, wind, distant hums, shifting animals, leaves brushing against each other. Even quiet environments are layered. Real silence is something the human brain rarely encounters, and when it does, it becomes striking because the absence feels louder than any noise could. If the world had fallen silent after a catastrophe, standing in that stillness would feel as though your senses were waiting for something to return that never quite does. It's strange to imagine Earth without us, without our routines, our noise, our constant movement and reshaping of the landscape. But in the aftermath of a global event, That's exactly what the world would feel like. Whatever structures remain would stand without purpose, slowly surrendering to temperature shifts, moisture, erosion, and time. Buildings aren't designed to exist without maintenance, and without life to reinforce them, they gradually lose the battle against their environment. Roads crack without anyone repairing them. Metals oxidize. Glass fractures under heat changes. Plastics weaken in sunlight. The silence after a catastrophe isn't just the absence of sound. It's the slowing of processes that depend on life, leaving behind structures that drift into decay, not because the planet is attacking them, but because nothing remains to keep them intact. The atmosphere would carry its own version of quiet. Without planes, vehicles, industry, or the constant upward drift of heat from human activity, the air patterns would feel muted. Clouds would still form, winds would still move, storms would still gather and break apart, but the small disturbances caused by billions of living creatures would be gone. Weather systems would feel broader, slower, more uniform in the way they shape themselves. The atmosphere is always in motion, but without living things shaping the lower layers through heat and moisture, that motion becomes smoother. It's still full of energy, but the sharpness goes away. In the oceans, the silence would feel different. Water doesn't fall silent in the same way air does. It continues to move through currents driven by temperature, salt content, and the rotation of the planet. Waves still rise and fall. Tides continue their steady cycle, but the noise of life disappears. No fish stirring sediment, no whales sending long calls through the deep, no coral reefs crackling with the sound of thousands of tiny creatures. The ocean becomes a place that feels detached from memory. Its movement persists, but the familiar activity that once filled it is missing. In deeper waters, where sunlight never reaches, the silence becomes even more pronounced. Hydrothermal vents still release heat and minerals, but the ecosystems that normally surround them may be reduced or gone entirely. In their place, the vents continue their steady release, unchanged by the silence around them. On land, the emptiness becomes more visible. Forests might remain as skeletal structures if fire or heat has stripped them bare. Grasslands might lie flat and colourless. Deserts might expand slowly without plant roots to hold sand in place. Some areas might be covered in ash, others might be flooded. The landscape becomes a record of what happened and what it erased. But even in this stillness, Earth isn't lifeless. It's simply adjusting. Everything that remains is responding instinctively to the new conditions. Heat disperses, water settles, soil reorganizes itself as minerals shift and settle under pressure. Rocks fractured by intense force continue to crack as they cool. The silence is only on the surface. Beneath it, the planet is still moving. What's remarkable about moments like this, if you can even call them moments considering how long they last, is that the planet doesn't view them the way we do. To Earth, this is just one phase among many. The silence after a catastrophe is not an ending, but a reset. The world has been through periods like this before. After asteroid impacts, after volcanic winters, after ice ages, after mass extinctions, the same quiet has settled across the world. And every time life eventually found its way back. This isn't a romantic reassurance. It's a geological fact. Earth has erased itself and rebuilt itself many times. What we call catastrophes are just turning points in its long story. Even in the deepest silence, some forms of life might persist. Microbial life has an extraordinary ability to survive conditions that seem completely uninhabitable. There are microbes that can withstand radiation levels that would destroy most known organisms, microbes that survive intense heat near volcanic vents, microbes that live kilometers beneath the surface of the Earth where sunlight and oxygen never reach. In the quiet after a global event, some of these tiny survivors may still be present, hidden in soil, ice, rock, or deep ocean trenches. They don't make noise, they don't shape the landscape in ways we see, but they hold onto the thread of life in ways that allow rebuilding later. If no complex organisms remain, the planet becomes a clean slate in terms of ecological development. That doesn't mean it's empty, it means the rules have changed. Without forests, oceans full of life, or animals roaming the surface, the planet reverts to its fundamental processes. Weather patterns disperse energy, water carves new paths, rock cycles continue, volcanic activity redistributes minerals, plate tectonics slowly rearrange the continents. This rearrangement happens whether life is present or not. The silence doesn't stop tectonic plates from drifting. It doesn't stop magma from rising. These processes continue because they're part of the planet, not the biosphere. If the catastrophe involved fire or intense heat, the air might carry particles for long periods, dimming sunlight and cooling the surface. If it involved an impact, debris would gradually settle, leaving layers of sediment that future scientists, if any exist, would one day study. If it involved climate collapse, the atmosphere might shift into a new equilibrium, one that feels inhospitable to anything familiar, but still capable of supporting life eventually. The silence after a catastrophe doesn't mean the world is suspended. It means it's between phases. As the days or years or centuries unfold in this quiet, the surface gradually begins to lose evidence of the event. Rain erodes ash, wind moves dust, rivers carry sediment to new basins, coastlines reshape as water finds new boundaries, mountains erode slightly, valleys deepen. Nothing returns to how it was before, but everything shifts towards stability. Stability is the first step toward rebuilding. The planet doesn't need life to reach stability. It only needs time. If you could observe the world during this shift, you'd start to see signs of transition. Not in the form of life returning, but in the way the land and water adjust to the new conditions. In some areas, the ground might warm enough for chemical reactions to begin forming more complex molecules. In others, minerals might dissolve into water, creating environments suitable for early biological activity. In the deep ocean, hydrothermal vents would remain some of the most active locations. They don't rely on sunlight or atmosphere. They rely on Earth's internal heat, something no catastrophe can fully extinguish. These vents may already be supporting microbial life, or creating new pathways that lead back to it. The silence lingers during all of this. It becomes a defining feature of the rebuilding phase. But eventually the quiet begins to thin. Small physical interactions create tiny disturbances, water dripping from newly formed ice, rocks cracking under heat or cold, sand shifting under its own weight. These sounds are microscopic compared to what once filled the world, but they signal something important. Silence never lasts forever. Noise begins to return long before life does. The world starts to rebuild its rhythm through physical processes alone. And from that rhythm, the conditions for something new begin to form, not immediately and not predictably, but in ways that follow the same rules that shaped the earliest version of Earth. The planet is recovering. The silence remains, but it's no longer the silence of an ending. It's the silence of a world that is preparing its next beginning. When a planet begins to recover from a catastrophe, the first signs of renewal are so small and so subtle that you could stand in the middle of them and never notice anything changing at all. Renewal doesn't announce itself. It doesn't arrive in a sudden burst of colour or in a dramatic shift from silence to life. It begins as a series of small, quiet processes, each one too minor to feel like a transformation on its own. But together, over long spans of time, they become the first sparks of a world learning how to rebuild. If you imagine looking at Earth in this state, you wouldn't see anything that resembles the life you know. There would be no plants stretching toward the sky, no animals moving across the land, no familiar signs of ecosystems returning. Instead, everything would look still. But that stillness is misleading, because underneath it, chemical reactions have already begun. Heat from the mantle continues to rise. Water continues to evaporate, condense and fall. Minerals continue dissolving, binding and transforming. These processes don't stop simply because the world has grown quiet. They're part of the planet's natural rhythm, a rhythm that keeps going even when life is gone. The earliest signs of renewal come from heat. Heat is one of the planet's most consistent sources of energy, and without life on the surface it becomes even more noticeable. Volcanoes still erupt, though perhaps not with the frequency they once did. Lava flows still cool into rock, steam still rises from geothermal vents. These vents, especially the ones deep in the ocean, provide chemical gradients that can drive the reactions necessary for complex molecules to form. Even if all surface life has been erased, these deep environments remain protected from surface conditions. They don't depend on sunlight, oxygen, or atmospheric stability. They rely on heat and minerals, and those never disappear completely. In the oceans, these hydrothermal vents create zones where chemical energy is abundant. Metals and sulfur compounds mix with seawater, producing the gradients that early microbes once depended on. And while the catastrophe may have wiped out existing ecosystems, the environment itself still holds the potential for new beginnings. Molecules bump into each other, react, break apart, and occasionally form structures that stand out from the chaos. The process is slow, but the planet doesn't measure time in days or years. It measures time in geological stability, and under those conditions, slow is enough. On the surface, sunlight becomes another ingredient in this quiet return. Even if the atmosphere has been heavily altered, it eventually clears enough for light to reach the ground. When sunlight hits certain minerals, it can drive reactions that help form the building blocks of life. Clay-rich regions, in particular, are excellent at trapping molecules and helping them organize into more complex structures. These clays provide surfaces where reactions can take place, protecting delicate compounds from being destroyed too quickly. Over long periods, these surfaces become laboratories for early chemistry. If water has returned to the surface, even in small amounts, it becomes another catalyst. Water dissolves minerals, carries them across distances, and deposits them in new environments. It creates pools where reactions can concentrate. It carves channels that bring different materials together. It warms in sunlight and cools at night, creating temperature cycles that influence how molecules behave. These cycles can help certain compounds assemble, break apart and rearrange themselves until something stable emerges. Stability is one of the prerequisites for renewal. The planet needs repeated interactions, repeated reactions, and repeated opportunities for new structures to form before anything resembling life can take hold. As minerals dissolve and recombine, elemental cycles begin to re-establish themselves. The carbon cycle slowly restarts as volcanic activity releases carbon dioxide into the atmosphere. Rain dissolves this carbon dioxide, carrying it into newly forming oceans where it reacts with minerals to create carbonates. Nitrogen begins circulating again as lightning or volcanic activity fixes atmospheric nitrogen into usable forms. These foundational cycles don't bring life back on their own, but they create the environment life needs. They create the chemistry that builds the stage for biology. The atmosphere during this time still might not be breathable. It could be full of carbon dioxide, sulfur compounds, or dust depending on the nature of the catastrophe. Oxygen may be nearly absent. But early Earth itself once had an atmosphere like this, and the first life forms emerged long before the air contained oxygen. If renewal is going to happen, it doesn't depend on oxygen at first. It depends on energy sources and chemical gradients, and those exist even in harsh environments. If the catastrophe left behind pockets of surviving microbes hidden deep underground or in ocean trenches, these survivors might begin to spread once conditions stabilize. Their reproduction would be slow, limited by available resources and extreme conditions, but even slow growth matters. A small population can expand over thousands or millions of years until it begins shaping the environment again. Microbes don't need much to survive. They don't need sunlight or complex ecosystems. They only need water, energy, and a few basic chemical compounds. If those exist, they begin the long process of rebuilding. But even if there are no survivors, the planet still finds ways to bring renewal. Chemical evolution is an inevitable outcome when energy and matter interact over long timescales. Molecules that form randomly can occasionally link together in ways that make them more stable. These stable structures persist longer and have more opportunities to participate in reactions. Some structures might store energy, others might catalyze reactions, others might form protective shells. Over time, these simple compounds can develop into more complex ones until eventually a self-sustaining system emerges. It doesn't happen quickly, and it doesn't happen predictably, but given enough time, it happens. On the land, the environment begins to shift. If the surface was scorched, ash and weathered rock start to break down, creating the earliest forms of soil. Wind carries dust into low-lying regions where it accumulates. Rain mixes with minerals, creating mud that dries and cracks. Each of these processes contributes to the formation of new landscapes. These landscapes don't look alive yet, but they hold the potential for future ecosystems. They shape how water flows, how heat is distributed, and how chemicals mix. Over time, valleys deepen, mountains crumble, and rivers carve their paths with more consistency. Stability increases, and stable environments are where renewal thrives. The oceans also begin to diversify. Temperature differences create currents that move nutrients across the water. Upwelling zones bring minerals from the deep ocean to the surface. These minerals might not feed life yet, but they prepare the environment for it. If sunlight reaches the surface, certain molecules can absorb it, storing energy that can later be used in chemical reactions. Over long periods, these reactions can give rise to structures that form the precursors to photosynthesis. The earlier steps are invisible, but they're essential. Without these building blocks, the complexity of life can't return. The atmosphere continues to adjust as well. The particles released by the catastrophe gradually settle. Weather patterns distribute gases more evenly. Clouds form and disperse in predictable cycles. Over time, greenhouse gases may trap more heat, warming the surface enough for liquid water to become more stable. Or the atmosphere may thin and cool, depending on how much carbon dioxide volcanic activity releases. Either way, the air moves toward equilibrium. Equilibrium is necessary not because life demands calm conditions, but because consistent conditions allow chemical processes to repeat themselves. Repetition is the bridge between chemistry and biology. If energy from sunlight drives some of the early reactions, these photochemical processes become the first hints of a new kind of metabolism. Molecules that absorb light and change shape can eventually lead to pigments. Pigments can lead to energy storage. Energy storage can lead to self-sustaining reactions. These steps are tiny. They take millions of cycles. But they are the sparks that push the planet from a chemically active world to a biologically active one. On the surface, the first signs of renewal might be the formation of simple organic films on rocks near water. These films wouldn't resemble anything alive, but they organize molecules into patterns that can support further reactions. In other areas, mineral surfaces might begin to show layers where organic compounds have adhered. These layers act as platforms for more complex chemistry. They trap molecules, concentrate them, and hold them together long enough for them to interact more effectively. In the oceans, renewal might look like strings of molecules that begin to fold in consistent ways. Folding gives molecules structure. Structure allows function. Function allows the earliest behaviors that resemble metabolism. It starts with simple reactions, energy in, energy out. But once these reactions are reliable, complexity can grow. Complexity doesn't arrive suddenly. It emerges because simpler systems that persist longer have more opportunities to evolve. And evolution, even at this early stage, begins the moment something can copy itself imperfectly. Imperfect copying means variation. Variation means some structures survive longer than others. The ones that survive longer accumulate more changes. Over eons, these changes lead to the first true living systems. They might be simple. They might be fragile. They might be nothing like the life that existed before the catastrophe. But they are enough. They are the first sparks of renewal manifesting as biology rather than chemistry. Once these early systems stabilise and spread, the environment begins to shift again. Organisms produce waste products that alter their surroundings. Some release gases, others consume minerals, others influence the acidity of water. These changes create new conditions that allow even more types of molecules and organisms to emerge. The biosphere slowly begins to rebuild itself, not through intention or design, but through countless small interactions that accumulate over unimaginable lengths of time. The world doesn't look alive yet, not in the way we recognise. But the chemistry beneath the surface is no longer just a series of reactions. It's a system, one that grows in complexity, stability and potential. The silence remains, but it's no longer the silence of emptiness. It's the silence that comes before the first faint echoes of life returning. A silence filled with the slow, steady sparks that set the stage for everything that comes next. Air and water never truly stop moving, even after a world-ending event, but the way they behave in the aftermath changes so drastically that it almost feels as though the sky and sea are trying to relearn how to exist. They don't snap back into balance. They don't immediately settle into familiar cycles. Instead, they begin a long negotiation with the altered planet beneath them. That negotiation becomes one of the most important steps in Earth's renewal, because the sky and sea together shape everything that happens afterward. Without stable air, chemical processes stall. Without stable water, energy can't spread in predictable ways. And without both working together, nothing complex can return. In the earliest stages of recovery, the atmosphere often becomes a record of whatever catastrophe reshaped the planet. If the event released dust, ash, chemical compounds, or fragments of rock, the sky might remain thick and dim for years, decades, or even centuries. These particles scatter sunlight unevenly, lowering global temperatures and slowing the warming needed to restart major cycles. If the event involved intense heat, gases might collect in the air that trap heat instead, pushing temperatures higher than anything the surface can handle. Either outcome results in instability, the kind of instability that makes it difficult for any new life to take hold, but not impossible for the planet itself to keep rearranging. As the atmosphere begins to settle, gravity pulls heavier particles downward. Lighter ones rise and disperse. Winds, still following the rules of fluid dynamics, push the remaining debris into thinner and thinner layers. Rain helps wash out particles that linger too long. Over time, the sky clears a little at a time, not in a sweeping transformation, but in small patches where conditions allow more light to break through. These patches expand slowly until sunlight reaches the surface with more consistency. Sunlight doesn't just illuminate the land. It warms the ground, creates temperature differences in the air, and begins pushing the atmosphere back towards cyclical patterns. Those cycles become the foundation for everything that comes next. As sunlight increases, the atmosphere divides into layers again, each with its own signature. The lower layer warms from the ground. The upper layers respond more to sunlight and space. Between them, convection cells begin developing stable circulation. These cells eventually form the familiar patterns of trade winds, westerlies, and polar easterlies, though they may not resemble the ones that existed before. Their shape depends entirely on the new geography created by the catastrophe. If mountain ranges have collapsed or new ranges have formed, the wind patterns shift accordingly. If the continents have moved, the cycles that shape temperature and moisture reorganize themselves around the new arrangement. Rainfall returns gradually. At first, precipitation is uneven and sporadic, driven mostly by whatever heat pockets remain. Some regions might experience long periods with no rain at all, while others might receive intense bursts that reshape the ground. Over time, these extremes begin to level out. The atmosphere redistributes moisture based on new temperature gradients and the shape of the land. Clouds reform in predictable bands. Storm systems regain structure. Lightning becomes a part of the cycle again, splitting nitrogen in the air and forming compounds that eventually settle into soil and water. This nitrogen plays a foundational role in the chemical environment needed for life to advance, just as it did when Earth was young. While the sky works on regaining equilibrium, the oceans are undergoing their own transformation. The sea doesn't rebuild in a single, unified process. It responds differently in different depths and regions. Surface waters, influenced most directly by sunlight and wind, change first. Heat from the recovering sun begins to warm the upper layers. As the surface warms, it expands slightly and becomes less dense. This shift creates a gradient between warm surface water and cooler deep water. That gradient drives mixing, upwelling and circulation, all of which are essential for distributing minerals and nutrients. If the catastrophe caused widespread ocean acidification or the loss of significant chemical balance, the sea would begin the slow process of rebalancing. Volcanic activity under the ocean releases minerals that neutralize acidity. Water cycles through deep-sea vents, picking up chemicals that alter pH levels. Sediment in the ocean traps compounds that might otherwise remain suspended. Over thousands of years, the ocean gradually shifts toward a composition capable of supporting the earliest chemical pathways that lead to life. Deeper beneath the surface, the water remains relatively stable. The deep ocean is insulated from many surface changes, especially from temperature fluctuations. Even if the upper layers are dramatically altered, the deep zones may retain conditions similar to those before the catastrophe. These stable regions act as long-term chemical reservoirs. They store minerals, heat, and dissolved gases that eventually resurface through slow circulation. This circulation is critical. It ensures the ocean doesn't stagnate. It distributes chemical ingredients evenly over time. Without circulation, the sea would develop isolated pockets of imbalance, making the return of complex chemistry far less likely. The boundaries between the sky and sea also begin to re-establish themselves. Evaporation becomes regular again once temperatures stabilize. Clouds form consistently above warm regions. Rain returns to the ocean, replenishing the upper layers. This exchange of water between sea and sky forms the water cycle, and even if it looks different in the aftermath of a catastrophe, it is one of the planet's most resilient systems. Once the water cycle is active, it helps regulate temperature, acidify or neutralize certain chemical mixtures, and distribute heat more evenly. In coastlines newly shaped by the event, tidal rhythms begin carving patterns into the land. Even if the moon's orbit changed slightly, or if Earth's rotation shifted, tides continue. Gravity ensures that. These tides can shape new marshes, beaches, deltas and estuaries. As water flows in and out of these areas, it lays down sediment in repeating layers. These layers eventually become habitats or chemical zones. They aren't habitats yet in the sense of supporting complex organisms, but they are dynamic environments where chemical interactions can occur repeatedly. Repetition under varying conditions is one of the key factors in the emergence of new complexity. In shallow waters near volcanic regions, geothermal activity plays a crucial role. Hot water filled with minerals rushes into cooler seawater, creating gradients that support reactions capable of producing simple organic molecules. These molecules might form on mineral surfaces or float freely in solution. Over long periods, they can combine, break apart, and recombine in ways that slowly increase their complexity. These processes don't rely on perfect conditions. They rely on consistent access to energy and raw materials. Geothermal zones provide both, making them some of the most promising places for the first signs of renewal. As these small sparks begin forming in the sea, the sky continues to influence how they develop. Sunlight acts as both a catalyst and a filter. It breaks down unstable compounds, leaving behind molecules that can better withstand environmental stress. Over time, these surviving structures begin to accumulate. At the same time, ultraviolet light can trigger the formation of certain organic compounds, especially if minerals like iron, silica, or clay are present. Some early photosensitive molecules might even begin forming in surface waters, storing a small amount of energy from sunlight. This stored energy provides another pathway toward complexity. Even though the sky and sea feel like separate worlds, they are constantly shaping each other. The atmosphere determines how much heat the oceans retain. The oceans determine how much moisture enters the sky. Wind patterns determine where rain falls. Evaporation determines how salty the seas become. Each cycle strengthens the others. When one stabilizes, it encourages the next. When all find balance together, the planet transitions from recovery into a state capable of supporting new biological development. As these processes continue, Earth's temperature begins settling into a predictable range. This doesn't mean comfortable or familiar. It simply means consistent. Consistency allows the chemical reactions in the oceans to occur repeatedly in similar conditions, increasing the likelihood of stable molecules forming. These molecules might cling to mineral surfaces, group together in clumps, or form delicate membranes. Any of these outcomes can be foundational to early life. Wind that once moved unevenly now follows recognizable routes. Ocean currents that once shifted unpredictably now form loops and gyres. Evaporation and rainfall spread heat around the planet more evenly. Over long stretches of time, ice caps might reform if temperatures allow, or they might melt if the catastrophe pushed the climate toward warmth. Either outcome still results in a balance. Earth finds its own version of equilibrium based on the new conditions. This equilibrium becomes the baseline from which life can attempt its return. Along coastlines, shallow water gradually becomes one of the most chemically interesting environments. As waves crash repeatedly against rocks rich in minerals, they release ions and compounds into the sea. These compounds dissolve, interact and settle in tidal pools where water evaporates and refills on a regular schedule. Tidal pools become natural laboratories. Temperature changes between day and night influence reactions. Mineral surfaces act as catalysts. Waves bring in fresh material. These cycles mirror some of the earliest environments on young Earth, making them promising zones for renewal. Meanwhile, in the atmosphere, gases produced by volcanic activity and chemical interactions begin forming stable ratios again. Carbon dioxide, water vapour, nitrogen, and traces of other gases gradually settle into a mixture sustainable for long-term climate cycles. Oxygen remains low or absent initially, but that doesn't prevent early chemical systems from developing. In fact, a low oxygen atmosphere protects delicate molecules from oxidation, giving them more time to persist. As the environment becomes more structured, the interplay between sky and sea intensifies. Warmer atmospheric regions create areas of evaporation. Cooler ocean water absorbs gases from above. These exchanges continue shaping the chemical landscape. Eventually, once enough stability emerges, the oceans become the primary cradle for new complexity. Molecules collide, self-assemble, and sometimes persist. Membranes form. Energy flows through simple chemical systems. Circulation keeps those systems moving, replicating, and evolving, even if only at a microscopic scale. While the sea begins hosting these first sparks, the sky isn't passive. It carries evidence of these changes in subtle shifts. Trace gases begin showing up in tiny amounts. Atmospheric composition starts to drift in response to the earliest forms of chemical metabolism. Nothing dramatic yet, nothing visible, just hints, but hints accumulate. In time, the sky and sea together form the climate engine that will eventually support more advanced life. They don't return to what they were before. They become something shaped by the new world beneath them, something stable enough to allow new chemistry, new growth, and eventually new ecosystems. The rebuilding of the sky and sea marks the point where the world shifts from surviving its catastrophe to preparing for everything that follows. Nothing about a reshaped world stays still for long, even if life hasn't yet returned to notice the changes taking place. Once the air and the oceans begin settling into their new patterns, the solid parts of the planet respond in their own slow and deliberate way. Mountains rise or collapse depending on the stresses they've absorbed. Rivers carve pathways through unsettled terrain. valleys deepen, basins fill, the ground reorganizes itself until it finds the shape that best matches the forces acting on it. In this quiet stage of Earth's recovery, the landscape becomes a record of both what happened and what the world is preparing to become. Across the planet, tectonic plates continue drifting. Their motion doesn't depend on life or surface conditions. It's driven by heat deep inside the mantle, heat that no catastrophe can extinguish entirely. That movement reshapes everything over long periods. If the event that altered the world changed the distribution of heat inside the planet, plate boundaries may shift. Subduction zones might speed up or slow down. Ridges where new crust forms might widen or narrow. Even a slight change in internal temperature can influence the rate at which plates move, and that rate determines how continents form and deform. The creation of mountains is one of the clearest examples of this ongoing change. Some mountain ranges may have collapsed under the force of the catastrophe, their peaks fractured into rubble. Others might have been uplifted further by the shifting plates below. If two tectonic plates continue pressing against each other, new ranges begin forming. They start as subtle bulges that grow over thousands of years into towering structures. These mountains don't look like the ones that existed before. Their shapes depend on the new pressures within the planet and the new arrangement of the continents. Volcanic mountains also play a role. If magma rises through weakened crust, new volcanic cones can appear where none existed previously. These cones might grow quickly in geological terms, releasing lava that cools into fresh rock. Over time, these fresh surfaces weather into dust and soil. Even without life, these early soils help determine how landscapes evolve. Water flows differently around them. Wind patterns shift. Temperatures fluctuate based on their height and position. Mountains, whether new or newly reformed, become anchors that influence everything around them. While mountains rise or change shape, rivers begin their own careful work. A river doesn't follow a single predetermined path. It follows gravity and the resistance of the ground beneath it. After a catastrophe, the terrain is often uneven and unstable. Rocks lie loose across slopes. Channels that once directed water may no longer exist. As rain returns in cycles, water begins choosing routes through this new environment. It pools in low areas, spills over edges, carves channels, and spreads sediment wherever the flow slows enough for particles to settle. These early rivers don't resemble the smooth, predictable waterways that support ecosystems in stable worlds. They shift frequently as loose soil and rock change position. A channel that forms one season might collapse the next. Over years, though, patterns emerge. Water finds the paths of least resistance and returns to them repeatedly. Those paths deepen into recognizable rivers. Where the ground resists erosion, cliffs form. Where the ground softens, riverbanks widen. Sediment carried downstream begins forming new floodplains. These floodplains won't support life yet, but they create a structured environment where chemical interactions can occur more reliably. In places where rivers meet newly formed seas, estuaries start to appear. These transitional zones between fresh and salt water create gradients of salinity, temperature, and sediment composition. Even without life, gradients like these influence which minerals dissolve and which settle out. Over long spans, these processes shape the chemistry of coastal regions. The interaction between river water and seawater becomes one of the first complex systems in the renewing world, one that continues, cycle after cycle, until biological systems eventually take advantage of it. Elsewhere on the planet, valleys form through erosion. Wind shapes expose rock into ridges and arches. Rainfall splits stone into fragments. Freeze-thaw cycles crack boulders into smaller pieces. Each change is slow, but none are insignificant. The land adjusts continuously. These adjustments matter because they determine where water flows, where minerals accumulate, and how energy spreads across the surface. Without stable landscapes, chemical systems have no consistent environment in which to evolve. The shaping of valleys, canyons, and uplands becomes part of the foundation for whatever comes next. The memory of the old world persists in these landscapes, even if nothing living remains to interpret the patterns. A collapsed mountain range still shows traces of the forces that once pushed it skyward. A buried riverbed reveals the pathwater carved long before the catastrophe. Layers of rock store evidence of ancient climates and ecosystems. The planet doesn't erase its history, it simply layers new stories over the old ones. If intelligent beings were to study this renewed Earth millions of years later, they would still find the remnants of the catastrophe embedded in stone, marked by unusual mineral layers or abrupt changes in sedimentation. One of the most important features of post-catastrophe landscapes is the way they influence climate. Mountains cast shadows that alter how heat is distributed. Basins collect water or hold cold air. Plateaus reflect sunlight differently than forests once did. All of these factors affect the atmosphere and the oceans. The new climate patterns emerging on the planet are shaped partly by the landscape that existed before, and partly by the new formations created during recovery. Over time, these patterns influence how temperature varies across the surface and how moisture circulates. If the catastrophe involved dramatic sea level changes, coastlines would appear unfamiliar. Low-lying land might remain underwater for long periods, forming shallow seas. These shallow areas are often chemically active. Sunlight penetrates them easily. Sediment settles in thin layers. Minerals dissolve into the water. All of this creates conditions where early chemistry can concentrate. In contrast, if sea levels fell dramatically, exposed seafloors would dry into broad plains cracked by heat and wind. These plains, rich in salts and minerals, could become sites where new chemical structures form as water evaporates repeatedly. Mountains also influence how rivers behave. Water flowing from high elevations carries minerals with it. As rivers descend, they slow down and drop heavier particles first. Lighter particles travel farther, creating layers of sediment sorted by size and composition. These mineral-rich sediments form regions where chemical interactions can accelerate. If future life is going to take hold, it often benefits from environments where minerals act as catalysts. Mountains, through erosion, provide those minerals in abundance. Meanwhile, underground processes continue alongside surface changes. Water seeps into fractures in the rock, dissolving minerals and creating new pathways. These underground channels can transport heat or chemicals over long distances, contributing to the overall reshaping of the landscape. Caverns might expand, underground lakes might form, pressure from shifting rock layers might trigger localized geothermal activity. These hidden systems add complexity to the environment, even if nothing living is present to interact with them. Over thousands of years, the combination of erosion, tectonic movement, and chemical change begins giving the planet a new identity. The landscapes that emerge are shaped both by the catastrophe and by the slow processes that follow. Some regions become mountainous and rugged. Others flatten out into wide plains. River systems settle into stable networks. Coastal areas find new boundaries. The entire surface of the world becomes organized enough for the next phases of renewal to take place. The memory of what once existed doesn't disappear, but it becomes part of the foundation for the world that's forming. Old mountain roots lift into new peaks. Sediments created by destroyed forests become the soil of future shores. Riverbeds carved long ago guide the creation of new waterways. Even without life, the planet remembers its past through the structures it leaves behind. At this stage, the landscape reaches a point where stability increases. Earth's crust cools into recognizable patterns of uplift and erosion. Rivers find long-term paths. Mountains reach heights that remain consistent for millions of years, eroding slowly. Coastlines become less chaotic. With this stability, the environment becomes more predictable. Predictability is one of the most important factors in the emergence of complexity. Chemical processes require cycles. Cycles require stability. Stability comes from landscapes that hold their shape long enough for repeated interactions to take place. As the world settles into this new configuration, the stage is set for deeper changes. The land is no longer shifting violently. The rivers no longer change course with every season. The mountains stand firmly enough to create long-term climate patterns. These climate patterns influence ocean currents, rainfall, and temperature. In time, they create niches that, while still empty, are ready to host new complexity. The renewed Earth is different than before, but not empty of potential. Its landscapes are full of environments waiting to interact with water, air, and energy in stable cycles. Mountains provide minerals, rivers distribute them, valleys collect them, coastlines mix them with seawater. Every slope, every shoreline, every fractured rock becomes part of the planet's slow preparation. With these structures in place, the world is ready to support the next forms of renewal. Nothing alive has returned yet, but the patterns that will make life possible again are growing stronger. The planet is not simply recovering, it is reorganizing itself into a place where complex processes have the stability they need to persist, grow, and eventually lead to the first fragile signs of a new biosphere. Air doesn't return all at once. It doesn't sweep across the planet in a grand shift or arrive with a sudden change in colour or clarity. Breathable air is something that forms slowly from countless chemical interactions, each one small on its own, each one taking place in an environment that may not yet seem ready for anything alive. When a world has been stripped of familiar life, the atmosphere becomes a mixture of whatever the catastrophe produced, whatever the crust releases, and whatever sunlight can alter. At first, these ingredients don't create air in the sense humans or animals could breathe. They form a blend that reflects nothing but aftermath. But over time, the atmosphere reshapes itself, not through intention or design, but through the gradual influence of physical cycles that push gases into new relationships. In the earlier stages of recovery, the air is often dense with particles, gases, and compounds that have no place in a stable, breathable atmosphere. If the catastrophe involved fire, combustion products hang suspended in the sky for long periods. If it involved volcanic activity, sulfur dioxide, carbon dioxide, and ash remain aloft, scattering sunlight and settling unevenly. If it involved chemical changes to the oceans or crust, those changes echo upward into the air. Whatever the cause, the atmosphere begins in a state far from anything that would feel safe to inhale. And yet this composition is temporary. Gravity pulls particles down. Rain binds some to the surface. Sunlight breaks others apart. The atmosphere doesn't stay in disarray forever. As the sky clears, the composition of the air gradually moves towards simpler mixtures. Water vapour cycles upward and downward with early weather systems, even if those systems are weak at first. Carbon dioxide becomes one of the dominant components, rising from the crust and oceans. Nitrogen remains present, usually in large amounts, because it is difficult to remove from an atmosphere once it accumulates. Nitrogen's inertness ensures it survives catastrophes that strip away other gases. So long before anything alive appears again, the atmosphere is already leaning toward a mixture of nitrogen, carbon dioxide, and water vapour. This mixture doesn't support complex life, but it provides a foundation that can be altered over time. Chemical cycles begin shifting as the planet stabilizes. Sunlight interacts with carbon dioxide, breaking it into reactive fragments. These fragments sometimes recombine into new molecules, and other times attach to minerals in the air or ground. Volcanic emissions continue supplying sulfur compounds, which gradually transform when they encounter moisture. Some of these transformations cool the atmosphere, others lead to acid rain. These cycles reshape the chemistry of the air step by step. None of them create oxygen yet, because oxygen requires either the presence of life or highly unusual geological activity. But these cycles bring the atmosphere closer to a state where oxygen could eventually accumulate. One of the most important transformations at this stage involves the oceans. As carbon dioxide accumulates in the air, it dissolves into surface waters. This dissolution helps regulate atmospheric levels while changing the chemistry of the sea. Carbon dioxide in water forms carbonic acid, which reacts with minerals and slowly reduces acidity over long periods. These reactions trap carbon in solid forms, removing it from the air. The reduction of carbon dioxide alone does not create breathable air, but it influences the planet's temperature. As CO2 levels fall, temperatures may drop as well, depending on how much heat the atmosphere is still trapping. The temperature shift changes wind patterns, water cycles, and weather, all of which influence how the atmosphere evolves. Lightning becomes a meaningful part of this chemical transition. As storms return, electrical discharges break nitrogen molecules apart, allowing them to bind with oxygen from carbon dioxide or other compounds. These reactions form nitrogen oxides, which eventually dissolve in rain. When these nitrogen compounds reach the ground or ocean, they participate in cycles that may later support early biological processes. Even without life, the atmosphere begins forming the precursors to nutrients that organisms will need in the distant future. The presence of these nutrients is another step toward an environment capable of supporting breathable air. The formation of clouds becomes more consistent as the planet cools. Clouds play a critical role in shaping the atmosphere's temperature and moisture content. They reflect sunlight from above and trap heat from below. They carry water between air and ground. They influence how quickly gases mix and how evenly they spread. If the catastrophe created long-term cooling, cloud cover may become dense and persistent. If it created warming, cloud patterns might appear chaotic and variable. Over time, though, these patterns stabilize into cycles that repeat with enough regularity to influence the chemistry of the air. Rainfall redistributes minerals and gases. When rain falls through an atmosphere rich in volcanic gases, it absorbs sulfur compounds, forming acids that reach the surface. These acids break down minerals in rock, releasing ions into rivers and seas. Some of these ions, such as iron and phosphorus, play important roles in future biological activity. Others bind to carbon or sulfur compounds, removing them from the air. Over thousands or tens of thousands of years, rainfall becomes one of the planet's main tools for refining the atmosphere. The more consistent the rain cycle becomes, the more stable the atmosphere grows. Meanwhile, the oceans themselves continue shaping the air. As temperatures stabilize, stratification patterns appear. Warm water rises to the surface. Cooler, denser water sinks. This circulation changes how gases dissolve and re-emerge into the atmosphere. Carbon dioxide dissolves more easily in cooler water. Methane trapped in sediments may escape through vents or cracks. These exchanges alter the upper atmosphere gradually. Without life-producing oxygen, these changes remain chemical rather than biological, but they still push the atmosphere into a direction more suitable for supporting complex processes. Eventually, after long stretches of chemical cycling, the atmosphere becomes dominated by nitrogen, carbon dioxide, and trace gases. Water vapor remains, but its levels fluctuate with climate. This mixture resembles the air of the very early Earth, a pre-oxygen atmosphere that supports chemical evolution but not breathing. For breathable air to return, oxygen must appear and accumulate. There are two main pathways for oxygen to enter the atmosphere: geological and biological. Geological pathways can create small amounts of oxygen through the breakdown of water molecules by ultraviolet light, but these amounts are usually too small to build a substantial layer. They create localized pockets, not a global envelope. So the return of breathable air requires the return of processes capable of producing oxygen at a rate greater than it is consumed. Before oxygen can accumulate, though, the planet must reach a stage where oxygen sinks are less dominant. Oxygen sinks are processes that remove oxygen from the air. They include reactions with iron in rocks, reactions with volcanic gases, and reactions with organic molecules. Early Earth absorbed oxygen quickly because its rocks were rich in reduced minerals. After a catastrophe, many of these minerals may reappear in newly formed terrain. So even if oxygen begins forming in small amounts, the planet consumes it immediately. Only when these sinks become saturated or less reactive can oxygen begin to rise. The first oxygen produced on a recovering Earth is often generated by simple photochemical processes. Sunlight breaks apart water molecules in the upper atmosphere, releasing hydrogen and oxygen. Hydrogen escapes into space because it is light. Oxygen remains. This process is extremely slow, but over long enough spans it contributes to the pool of available oxygen. It does not create a breathable atmosphere on its own, but it prepares the environment for the next shift. If early chemical systems in the oceans begin forming structures that resemble primitive metabolic cycles, some may eventually tap into light as an energy source. This does not require full photosynthesis. It only requires simple molecules capable of absorbing sunlight. Over time, these molecules become part of chemical pathways that transform the surrounding environment. If these early systems begin producing oxygen as a byproduct, the atmosphere starts accumulating it very slowly. These first oxygen-producing systems aren't true organisms yet. They are chemical structures that perform reactions repeatedly, because they are stable and energetically favourable. Once the oceans stabilise enough for primitive cellular structures to form, the potential for biological oxygen production increases. If early photosynthetic organisms arise, organisms that use sunlight to split water and store energy, they begin releasing oxygen into their surroundings. These organisms would likely resemble the earliest photosynthetic microbes on young Earth. They are simple, small, and slow to spread, but they influence the atmosphere with every cycle of sunlight they capture. The oxygen they release reacts immediately with dissolved iron or volcanic gases, but as time passes, these reactions gradually use up the available sinks. When oxygen sinks become saturated, oxygen begins remaining in the water and eventually escapes into the air. This transition marks the beginning of true atmospheric oxygenation. The shift is slow at first. Trace amounts accumulate in shallow waters where sunlight is strongest. These pockets of oxygen gradually mix with the broader ocean. Once oxygen reaches the air, ultraviolet light transforms some of it into ozone. Ozone forms a thin layer in the upper atmosphere, protecting the surface from harmful radiation. This protection allows more chemical systems and eventually more organisms to establish themselves near the surface. As photosynthetic microbes spread, oxygen production increases. At first, oxygen levels rise only slightly because geological processes continue consuming large amounts, but eventually, the rate of production exceeds the rate of consumption. The air begins accumulating oxygen in measurable amounts. Even small increases in oxygen transform the planet's chemistry. Iron minerals rust, methane in the atmosphere decreases, greenhouse effects shift, global temperatures adjust. These shifts influence climate patterns, ocean circulation, and the behaviour of storms. Over millions of years, oxygen levels climb. They do not rise steadily. They spike and plateau repeatedly as different parts of the planet adjust. Each spike allows new forms of early life to take advantage of oxygen in their energy pathways. These life forms consume organic molecules more efficiently. They grow, divide, and spread. Their activity increases oxygen fluctuations. As oxygen slowly becomes a stable component of the atmosphere, the planet enters a stage where breathable air is possible. A breathable atmosphere doesn't mean identical to the one lost in the catastrophe. It simply means an atmosphere capable of supporting organisms that rely on oxygen-based metabolism. The composition might differ in proportions of carbon dioxide, water vapour, or trace gases. Temperatures might be warmer or cooler. Pressure might vary based on the planet's new layout, but oxygen becomes a permanent fixture, rising slowly until it supports ecosystems far more complex than the chemical systems that created it. Once the air reaches this stage, the sky begins carrying the signs of renewal, not just in its chemistry, but in its appearance. Clouds form with greater regularity. Weather patterns adopt long-term structures. Winds distribute heat and moisture across stable landscapes. Rainfall creates cycles that support the growth of early life. The ozone layer reduces ultraviolet radiation enough for organisms to inhabit shallower waters and eventually expose surfaces. Breathable air marks not an endpoint but a transition. The atmosphere becomes the medium through which life interacts with climate, temperature, and energy. The planet is no longer in the quiet chemical stage of renewal. It is preparing for the next phase, where living systems begin shaping the environment as much as the environment shapes them. Life never restarts with a dramatic moment. There is no sudden spark that fills an empty world with movement or colour. No single event signals the beginning of a new biological era. Instead, the reawakening of life after a catastrophe is built from countless tiny steps, most of them so subtle that the planet itself barely seems aware of them. What looks like emptiness from a distance is full of chemical motion. What feels like a silent, lifeless world is already busy reorganizing itself into the conditions that allow life to return. The threshold between non-life and life isn't a clear dividing line. It's a slow transition where chemical systems begin behaving in ways that make persistence possible. When the earlier stages of reawakening begin, the world still seems barren. Mountains remain quiet and unmoving. Rivers continue carving their way through rock without any biological assistance. Oceans cycle heat and minerals with no plankton, no fish, no drifting webs of organic activity. And yet, beneath the stillness, the planet has been preparing for this moment for millions of years. Breathable air is beginning to accumulate. Water cycles are predictable. Temperatures shift within ranges that allow chemistry to repeat itself. The surface is no longer chaotic. It is no longer recovering from immediate trauma. It is settling into recognizable rhythms, the kind of rhythms that form the foundation of early biological systems. The first forms of returning life, or the earliest proto-life if nothing survived the catastrophe, are not creatures in the way people usually imagine. They do not swim, crawl, bloom, or behave. They are chemical structures that gain stability through repetition. Simple molecules in water begin forming more complex combinations. These combinations persist longer than their surroundings would normally allow. Some structures trap energy in predictable ways. Others become templates that encourage the formation of copies. These aren't living organisms, but they display traits that push them closer to life with each cycle. In tidal pools newly sculpted by rivers and oceans, minerals collect in thin layers. Water evaporates during warm periods, leaving behind concentrated mixtures of compounds. When the tide returns or rain falls, those compounds dissolve again, collide, separate, and regroup. Heat from sunlight changes reaction speeds. Cool evenings slow them down. These cycles sort through chemical possibilities over and over. Most structures fall apart quickly. A few persist. The ones that persist become starting points for more complex interactions. The planet is experimenting blindly through chemistry, and time is the only requirement for success. Hydrothermal vents remain another crucial site for reawakening. These deep-sea environments rely on heat from Earth's interior rather than sunlight. They create chemical gradients that fuel reactions simply because hot, mineral-rich water meets cold seawater. In these zones, simple molecules can form into chains. Chains can fold into structures that store energy. Those structures can interact with minerals in ways that produce simple metabolic cycles. Even without oxygen, light, or organic carbon, these systems can persist for long periods. They're not alive, but they make it easier for lifelike reactions to become part of self-sustaining networks. If any microbial life managed to survive the catastrophe, hidden underground, shielded within rock fissures, protected beneath thick layers of sediment, or clinging to the walls of deep ocean vents, these survivors now gain opportunities to spread again. Microbes don't need complex ecosystems to thrive. They need energy sources and raw materials. The recovering Earth provides both, even if only in small quantities. Early survivors might metabolize minerals, hydrogen, methane, or simple carbon compounds. Their populations grow slowly, limited by resources and environmental constraints. But slow growth is still growth. Over geological timescales, even sparse activity can reshape surroundings. Underground systems, often overlooked, can become the first living reservoirs. Water trickling through rock fractures brings dissolved minerals to places shielded from harsh surface conditions. If microbes lingered there, they could expand outward as conditions improve. If no microbes survived, minerals in these regions might still facilitate new chemical pathways. High-pressure environments allow reactions that surface conditions do not support. Over time, these hidden chemistries contribute to the pool of possibilities that eventually lead toward new biological activity. As oxygen begins accumulating in shallow waters, and eventually in the atmosphere, new forms of chemistry become possible. Oxygen allows energy to be extracted from molecules more efficiently. Microbes capable of using oxygen would thrive compared to those limited to anaerobic metabolism. But before complex metabolism can develop, early chemical systems need to adapt to the presence of oxygen, because oxygen is reactive and destructive. In the beginning, most early cells or protocells would avoid oxygen altogether. Only when oxygen levels reach stable, very low concentrations can early biological systems begin experimenting with it. The first biological reawakening likely resembles the earlier stages of life on young Earth. Simple cell-like structures form from membranes that arise in water containing certain lipids. These membranes aren't perfect. They trap molecules in unpredictable ways. But occasionally a membrane encapsulates a set of molecules capable of performing simple metabolic reactions. These primitive protocells are fragile. Many burst immediately when encountering salinity changes or temperature shifts, but some remain intact long enough to divide or fuse with other protocells. Fusion creates opportunities for combining internal components in new ways. Division creates opportunities for imperfect copies. Imperfect copying is one of the central steps toward life. Perfect copying creates identical outcomes that don't evolve. Imperfect copying allows variation. Variation allows selection. Selection allows improvement. Improvement allows survival. Survival allows expansion. With each cycle of copying and variation, protocells become slightly more suited to their environment. Over long periods, these cycles lead to systems that display increasingly lifelike behavior. Shallow seas offer environments where sunlight can influence these early systems. If certain molecules absorb light more effectively, these systems gain advantages. Light absorption becomes a way to store energy temporarily. Stored energy fuels reactions inside protocells. Some of these reactions create molecules that reinforce the membrane. Others create molecules that encourage copying. Over time, this leads to the earliest form of photosynthesis, though primitive and inefficient. But even inefficient processes matter when millions of years are available. Once early photosynthetic systems stabilize, they become major contributors to atmospheric change. Each cycle of sunlight stored and oxygen released incrementally raises oxygen levels, though the planet still consumes most of it through reactions with minerals. Slowly, these sinks saturate. The air begins holding more oxygen. Oceans begin carrying more dissolved oxygen. Regions near coastlines become environments where slightly more complex life forms have opportunities to take hold. The earliest microorganisms at this stage are almost nothing like modern bacteria or algae. They are simple, slow, often limited to narrow ranges of temperature and acidity. But they possess stable metabolic cycles. They can repair their membranes. They can replicate with moderate accuracy. They respond to chemical gradients. They migrate weakly toward energy sources. These behaviors don't require intelligence. They arise from the structure of molecules and the physics of their environment. And yet, they represent the first true signs that life is no longer theoretical. It is happening. As populations of these early organisms grow, their collective activity begins altering their surroundings. They consume carbon dioxide or other compounds. They release oxygen or methane or sulfur byproducts. These releases change the chemistry of their environment. Over time, many microorganisms die and settle into sediments. Their remains form layers that slowly accumulate in shallow basins. These layers become some of the first biological markers of the New World. They also trap carbon and other elements in ways that influence long-term atmospheric composition. Life's reawakening is not a smooth or predictable process. It involves countless setbacks. Early metabolic pathways collapse, membranes rupture, chemical imbalances wipe out entire regions of protocells, shifts in temperature destroy fragile structures. But failures are temporary because conditions keep repeating. Each new cycle presents fresh opportunities for molecules to assemble, persist, and adapt. Very gradually, resilience increases. Forms that survive one challenge are more likely to survive the next. In certain environments, stromatolite-like formations may begin developing. These layered structures form when microbial mats trap sediments. The mats grow upward as sediment accumulates, creating distinct layers. These structures represent stable, long-term communities of microorganisms. They don't resemble anything human eyes normally associate with life, but they are among the earliest coherent ecosystems a planet can produce. Their presence drastically alters local chemistry. They create pockets of oxygen-rich water. They influence mineral cycles. They provide habitats for other microorganisms. Over millions of years, life spreads from these early strongholds. Microorganisms colonize river mouths, shallow coastal areas, and eventually deeper zones as oxygen becomes more available. Some adapt to live near geothermal vents where chemical energy remains abundant. Others move into tidal pools where temperature swings force rapid metabolic adjustments. With each new environment colonized, variation increases. Variation fosters innovation. Innovation leads to metabolic transformations that make new ecosystems possible. The transition from water-based life to life capable of interacting with the land is far in the future, but the groundwork is forming now. Sediments laid down by microorganisms accumulate in patterns that will eventually form the soil needed for land ecosystems. Chemical interactions between life and rock begin altering minerals. These changes are so subtle at this stage that they cannot be seen, but they matter because they prepare the surface for later generations of organisms. Oxygen continues to accumulate, though still slowly. This slow increase permits more advanced metabolic pathways to evolve. Organisms capable of using oxygen efficiently gain enormous advantages. They can extract far more energy from their food sources. Energy efficiency translates into faster replication, greater resilience, and more complex biochemical processes. These processes eventually lead to more varied forms of cellular life. As life spreads across the oceans, the chemical structure of the world continues shifting. The air becomes clearer. The sea becomes more chemically diverse. Rivers carry increasing amounts of organic molecules downstream. Coastal sediments fill with the remains of microorganisms whose success was matched by their fragility. Everything begins moving toward greater complexity, but the transition is gradual. Nothing leaps suddenly. Life builds itself from the smallest possible building blocks, one cycle at a time. Eventually, ecosystems begin forming. At first, these ecosystems exist only at microscopic scales. Microorganisms compete for minerals, sunlight, and chemical gradients. Populations rise and fall with the seasons. Over time, certain species, or precursors to species, begin to dominate particular environments. These early dominances create pressure on other organisms to adapt. Adaptation leads to diversification. Diversification leads to interactions that are more complex than simple survival. These interactions begin shaping the environment in ways that can be felt on a planetary scale. Oxygen levels rise more consistently. Methane cycles shift. Cloud formation changes. Temperatures alter slightly. These changes influence wind patterns, which influence ocean currents, which influence temperature gradients, which influence ecosystems again. Life and environment become locked into a feedback system, each one pushing the other toward new states. At this point, The world is no longer empty. It is no longer defined by silence or chemical simplicity. It has entered a stage where life, no matter how basic, is fully part of the planet's identity again. The catastrophe no longer defines the world. The recovery defines it instead. The first hints of ecosystems have taken root. The earliest communities of organisms are shaping the environment as much as the environment shapes them. The cycle of renewal has crossed the boundary between chemistry and biology, and in this new balance, the world is ready for the next transformation. The reawakening has begun, not with a sudden moment, but with a long sequence of small, persistent steps that carry life from the edge of nothing into the beginnings of a new era. Oceans do not consciously choose anything, yet the way they assemble life after a catastrophe can look almost deliberate. They create gradients, cycles, pressures, and environments that force living things to adapt or disappear. They isolate some chemistry while mixing others. They stabilize certain molecules while breaking apart ones that cannot handle their rhythms. In time, these patterns determine which organisms can survive and which cannot. When a planet is rebuilding, the ocean becomes the single most influential environment for deciding the future direction of life. Its currents, temperatures, mineral content, and sunlight exposure create a complex series of filters, and only the structures that fit these conditions manage to persist. At the beginning of this stage, the oceans remain relatively quiet. They have circulation, waves, and chemical activity, but none of the movement is driven by living organisms. There is no plankton influencing nutrient cycles, no algae forming dense mats, no animals stirring the water as they migrate. The sea behaves entirely according to physics. Temperature differences move water across basins. Salinity gradients shift layers upward or downward. Minerals from vents and eroding landscapes disperse slowly. Even without biology, these patterns create order, and order is essential for the emergence of new forms of life. Chaos makes it difficult for early organisms to stabilize. Order, even if imperfect, provides predictable conditions. The earliest life forms to reappear after the catastrophe remain microbial. They drift in currents or anchor themselves to mineral surfaces. Their success depends almost entirely on how well they respond to temperature, salinity, pressure, and chemical availability. In shallow waters, sunlight influences growth. In deeper regions, chemical gradients fuel metabolism. The ocean does not guide these organisms intentionally, but it shapes their opportunities. If a certain region has more iron, for example, microorganisms that use iron-based metabolism gain an advantage. If a region has more light, photosynthetic organisms grow faster. Over time, these advantages accumulate and create the beginnings of biological structure. Different parts of the ocean favour different kinds of organisms. Warm, shallow waters near volcanic islands create environments where minerals and sunlight interact, forming ideal conditions for primitive photosynthesis. These regions support early metabolic pathways that release oxygen or other byproducts into the water. As these pathways stabilize, populations expand. The growth of simple photosynthetic organisms creates a ripple effect. More oxygen dissolves into the upper layers of the ocean. Minerals that react with oxygen begin transforming. The chemical landscape shifts. Other organisms evolve to take advantage of the new conditions. In this way, sunlight indirectly encourages diversity. Cold, nutrient-rich regions near upwelling zones support a different kind of early life. Here, deep water rises to the surface, bringing minerals with it. These minerals feed microorganisms that rely on chemical reactions rather than sunlight. Their metabolism might use sulfur, hydrogen, methane, or metal ions. These organisms do not compete with photosynthetic organisms directly. Instead, they occupy a complementary niche. As upwelling continues cycle after cycle, these chemosynthetic life forms build small communities around mineral-rich zones. These communities provide stability for early food webs long before anything resembling animals appears. Deep-sea vents continue shaping the fate of life. Vents create extreme conditions that favour organisms capable of withstanding temperature shocks, chemical gradients, and high pressures. These organisms replicate slowly but reliably. They form biofilms on rocks near vents, creating patches of microscopic ecosystems. Over long periods, these ecosystems influence the surrounding water chemistry. They release compounds that drift away from the vent, forming trails of nutrients. Other microorganisms migrate along these trails, following the resources. This movement spreads early life across the ocean floor in small increments. Coastal zones become the most dynamic environments in the recovering ocean. Tides repeatedly flood and drain shallow areas, causing cycles of concentration and dilution. Organisms that survive these shifts must adapt to fluctuating salinity, temperature, and oxygen levels. While these conditions might seem hostile, they create unparalleled opportunities for evolution. Environments that change predictably force organisms to become more flexible. Flexibility ensures survival when the planet undergoes further shifts. Over time, coastal microorganisms diversify faster than those in deep, stable waters. Each new variant carries slightly different metabolic pathways, membrane structures, or replication methods. As oxygen accumulates in specific regions, the ocean begins forming layers based on oxygen content. Upper layers contain more oxygen, because photosynthetic organisms concentrate near sunlight. Deeper layers remain anoxic for long periods. These layers determine which organisms can evolve and where. If an organism can tolerate oxygen, it moves into the upper zone, where energy availability is higher. If it cannot, it remains in deeper regions. Over time, this separation creates distinct branches of early evolution. Life begins to specialize. Specialization becomes one of the ocean's primary tools for choosing its creatures. Whenever chemistry shifts, organisms that adjust survive. Those that cannot either perish or retreat into narrow environments. For instance, when oxygen continues to accumulate, organisms that rely on anaerobic metabolism face pressure to evolve defenses. Some develop enzymes that neutralize reactive oxygen species. Others shift their metabolic pathways. These responses allow them to expand into more regions. Meanwhile, organisms that cannot adapt remain confined to deep sediments or hydrothermal vent systems. The ocean creates opportunities and barriers at the same time. Temperature gradients play a similar role. In warm waters, metabolic reactions proceed quickly. Organisms that can replicate at higher speeds gain advantages. In cold waters, reactions proceed slowly, favouring organisms that invest energy in stability rather than growth. These different strategies lead to long-lasting evolutionary branches. Warm water communities become hotspots for rapid diversification. Cold water communities become anchors of ancient stable lineages. Both forms influence the future of marine ecosystems. Salinity patterns add another layer to this selection process. As rivers reshape landscapes, they carry minerals and salts into the sea. Some regions become saltier than others. Organisms that tolerate high salinity occupy these regions. Others avoid them. This separation ensures diversity. When conditions eventually shift, whether due to climate change, tectonic movement, or sea level adjustments, organisms that once lived separately encounter each other again, creating new opportunities for genetic and metabolic exchange. Currents move early organisms around the planet, distributing them unevenly. Some regions become dense with microbial life, others remain sparse. Currents create invisible highways that connect ecosystems. A microorganism from a warm, shallow region may travel thousands of kilometers and arrive in a cold upwelling zone. If it survives the transition, it may introduce new metabolic pathways to the local community. These exchanges, though rare at first, become more common as currents stabilize. They help unify the ocean's chemistry and accelerate evolution. Early ecosystems begin forming on the seafloor. Microbial mats spread across rocks and sediments. These mats create layers of activity. Some layers rely on sunlight filtering through the water, others rely on chemicals rising from below. These layers interact, sharing nutrients and byproducts. Over time, these mats become complex enough to influence the water around them. They trap sediments, form porous structures, and create microhabitats. These microhabitats become breeding grounds for metabolic diversity. Each pocket of water within these structures provides slightly different conditions. Over long periods, these variations create numerous opportunities for new forms of life. As oxygen continues increasing in the surface waters, organisms capable of aerobic metabolism gain an advantage. Aerobic metabolism produces more energy per molecule of food. This efficiency allows cells to grow larger, store more energy, or divide more frequently. Aerobic organisms spread rapidly wherever oxygen becomes stable. Their activity increases oxygen fluctuations at first, but eventually helps stabilize it. They consume organic matter more efficiently, clearing environments that would otherwise stagnate. Their presence reshapes the chemical landscape in ways that favor even more complex forms of life. The evolution of predatory behavior begins long before true predators appear. Some microorganisms evolve mechanisms to attach to others and extract nutrients. These early interactions push both sides toward innovation. Prey organisms develop defensive membranes or chemical deterrents. Predatory organisms develop stronger attachment structures or specialized enzymes. Even at the microscopic level, the ocean becomes a place of interaction rather than simple metabolic activity. The shifting balance of pressure and opportunity creates environments where diversity flourishes. Over time, simple colonies become more structured. Some microorganisms form chains or clusters. These arrangements provide protection from environmental shifts. They also allow specialization within the group. Some cells focus on gathering nutrients. Others focus on structural integrity. These early divisions of labor lay the groundwork for multicellular evolution. Multicellularity does not emerge suddenly. It begins with small cooperative behaviors that become more stable over generations. The ocean encourages this stability by providing environments where cooperation leads to higher survival. Once multicellularity begins its slow path, the ocean becomes a canvas for complexity. Larger organisms evolve gradually, shaped by their environment. If an area has abundant sunlight and nutrients, photosynthetic multicellular organisms may dominate. If another area has abundant chemical gradients, multicellular chemosynthetic organisms evolve. Each region supports different forms of early complexity, because each region's conditions differ in subtle but important ways. As time stretches forward, the ocean becomes full of small but noticeable forms of life. They are not yet plants or animals, but they are more than simple cells. They drift, anchor, divide, and respond to their environment with increasing sophistication. Their activity changes water chemistry. Their remains settle into sediments, forming distinct layers. These layers influence mineral content, which in turn influences future organisms. The oceans continue shaping life by reorganizing themselves. Currents shift when continents move. Sea levels rise or fall when climate changes. Volcanic eruptions release new minerals. Each change forces organisms to adapt again. The species that survive become the ancestors of more advanced forms. The species that cannot adapt disappear, leaving behind chemical signatures in sediments. Over millions of years, the ocean becomes home to ecosystems far more complex than anything that existed before the catastrophe. Photosynthetic organisms create oxygen-rich zones that support aerobic organisms. Chemosynthetic regions become strongholds for unique lineages that thrive in darkness. Coastal ecosystems transform tidal pools into nurseries of rapid evolution. Deep ocean ecosystems host stable communities that change slowly. All of these influences combine to determine which organisms rise and which fade. By the time diversity becomes visible through increasingly complex multicellular life, the ocean has already spent millions of years filtering, encouraging, challenging, and reshaping the conditions of survival. In this sense, the ocean chooses its creatures indirectly. It provides countless possibilities but only supports the ones that match its patterns. Its temperature, chemistry, and motion become the deciding forces. Through these forces, the sea remakes the living world, guiding it slowly and persistently into its next era, ready for the forms of life that will soon emerge from the stability it has created. Forests do not reappear quickly. They do not rise from the ground in neat, rapid succession, or reclaim a silent world in bursts of green after the catastrophe has passed. Their return is one of the slowest parts of a planet's recovery, because forests depend on stability, on cycles that repeat reliably, on layers of life that build on top of each other. Before a single tree can take root, the world must prepare conditions that trees depend on. Air rich enough in oxygen to support complex metabolism, soil capable of holding water and nutrients, climate stable enough to allow long-term growth. For forests to try again, the entire planet has to become a place where complexity can safely unfold. The earliest stages of this transformation take place long before anything resembling a plant exists. Soil formation begins as rocks, reshaped by the catastrophe, start to break down. Rain falls onto sharp, barren surfaces and dissolves minerals. Rivers carry fragments to new basins. Wind scours cliffs and deposits dust across lowlands. Temperature shifts crack stone into smaller pieces as hot days expand minerals and cold nights contract them. Each fragment becomes the beginning of soil, although this early soil is chemically primitive. It has no organic matter, no structure, no microbial networks. It is simply a mixture of particles waiting to be altered by the return of life. As microorganisms spread across the recovering oceans, some eventually begin colonizing damp surfaces near shorelines and riverbanks. These microorganisms are simple compared to any known plant, but their presence influences the formation of soil. When they die, their remains mix with mineral particles. Over long spans, these remains contribute organic matter, the subtle beginning of fertile ground. Soil enriched by microorganisms gains the ability to retain water longer, hold nutrients, and buffer chemical changes. Without these early microbial layers, no plant could survive, let alone a forest. The foundations of forested landscapes begin invisibly, with microbial films that alter the chemistry of the land grain by grain. Algae-like organisms, evolving from earlier photosynthetic life in the oceans, begin making their way onto land when shallow waters recede, or when coastal regions become moist but not fully submerged. These pioneers do not resemble mosses or lichens yet, but they form thin mats on rocks. They anchor themselves with simple filaments, allowing them to resist wind and water. As they spread, they trap dust, sand, and small particles. Their presence increases moisture retention. More importantly, they create conditions that allow more complex cells to join them. Over time, these early land-dwelling organisms form layered mats capable of surviving brief periods of dryness. These microbial mats mark the first direct interaction between life and land in the New World. They darken the surface, absorbing more sunlight. They release oxygen. They stabilize loose sediment during rainfall. With every cycle of growth and decay, they thicken the early soil. Their influence extends far beyond their size. They are the first step toward vegetation, because they change the planet's surface enough to allow future pioneers to take hold. Without their continuous work, forests would have nothing to grow from. Eventually, groups of early photosynthetic organisms evolve structures that allow them to resist desiccation for longer periods. These structures might be simple, protective coatings, thicker cell walls, or primitive mechanisms for controlling water loss. Their ancestors once drifted freely in oceans or lakes, but now they cling to the surface of damp rocks and soils, pushing slowly toward independence from constant water immersion. These organisms begin resembling something closer to modern microbial mats and lichens, though still far more primitive. Their continued spread increases the organic content of soils. As soils deepen, they begin forming layers. pockets of moisture, grains of differently sized particles, and concentrations of minerals. Over geological time, these mats give rise to organisms that resemble early moss-like structures. They form small, soft carpets near water's edge. These proto-mosses cannot grow tall. They cannot transport water internally. They remain limited to environments where moisture is constant, but they represent a significant leap forward in the complexity of life on land. With each layer of growth and decay, they enrich the soil further. Their roots, or root-like structures, break down rock faster than microbes alone ever could. Soil becomes richer, thicker, more capable of supporting other forms of life. As oxygen levels continue to rise and climate stabilize, new evolutionary opportunities emerge. Organisms begin developing vascular structures that can transport water internally. These structures do not appear suddenly. They start as tiny channels that move water by capillary action. Over millions of years, these channels grow more efficient, allowing early plant-like organisms to rise slightly off the ground. Height, even a few centimeters, provides advantages. Taller structures reach light more effectively. They disperse reproductive cells across wider areas. They avoid being smothered by sediment. As these early vertical organisms spread, they reshape their surroundings. The first small forests of the renewed world are not forests in the familiar sense. They consist of waist-high plants with simple stems and branching structures, dotting floodplains and moist valleys. Their reproduction depends on water, so they cluster in regions where rainfall is regular. They lack leaves as humans would recognize them. Instead, they have photosynthetic surfaces along their stems. Their presence begins altering the planet significantly. When clusters of these plants cover an area, they stabilize soil, making erosion less extreme. Their decaying remains feed the next generation. Their photosynthetic activity increases oxygen production. They influence climate at local scales by shading the ground and reducing temperature extremes. As time moves forward, evolutionary branches diverge. Some plants develop more sophisticated vascular tissues. These tissues allow them to transport water and nutrients more efficiently. With improved transport, plants can grow taller, anchor themselves more firmly, and withstand drier conditions. Height becomes an advantage in competing for sunlight. Taller organisms cast shadows that shape the environment for others. Those unable to tolerate shade evolve strategies for living in brighter regions, while others develop tolerance for lower light. The earliest hints of ecological competition begin shaping future ecosystems. Leaves emerge gradually. Early leaves are small and simple. They begin as tiny extensions that increase surface area. Over time, these extensions flatten into broader structures, capturing more sunlight and increasing photosynthetic efficiency. Leaves change the balance of life dramatically. Plants with leaves gain a significant advantage over those without them. They grow faster, store more energy, and spread more rapidly. As leaf-bearing plants multiply, the atmosphere receives more oxygen, and the land receives more shade. These changes influence temperature, soil moisture, and local climate patterns. Roots, at this stage, become increasingly complex. Early plants had root-like structures, but true roots evolved from tissues specialized for absorbing minerals, storing nutrients, and anchoring plants deeply. Roots begin forming networks below the surface, connecting individual plants through soil interactions. These networks stabilize entire hillsides, preventing erosion and allowing more soil to accumulate. Forest foundations form not above ground but below it, through roots that create an underground web. The soil becomes deeper, layered with organic material, and capable of supporting taller organisms. With stable roots, efficient leaves, and robust vascular systems, plants evolve into organisms that can grow several meters tall. These early trees do not resemble modern species, but they create environments where taller canopies begin forming. Canopies influence wind patterns, keeping moisture near the surface. They trap humidity, making regions beneath them more hospitable to smaller plants. They reduce temperature fluctuations. In this way, early forests become climate stabilizers. Their influence extends far beyond their trunks and branches. Forests transform river systems as well. Their presence reduces the speed of water runoff, allowing rivers to flow more steadily. They filter sediment, clearing water in some areas and depositing minerals in others. Riverbanks become lined with vegetation that anchors the soil. Floodplains fill with organic rich material deposited during seasonal floods. These floods carry seeds, simple at first, more complex later, across large distances. Forests spread by riding the rhythms of rivers. As complexity increases, forests begin expanding into drier regions. Plants evolve waxy coatings that reduce water loss. Some develop seeds capable of surviving long periods of dryness before germinating. Others evolve mechanisms to store water internally. Forests no longer remain limited to wet valleys and coastal plains. They begin covering hillsides, plateaus, and interior basins. Their growth patterns depend entirely on climate. In areas where rainfall is predictable, dense forests form quickly. In areas where rainfall is sporadic, open forests or shrublands appear. The world becomes divided into regions defined by vegetation. Competition intensifies. Plants evolve strategies to outgrow competitors, taller trunks, broader leaves, deeper roots. Others evolve efficiency, surviving with fewer resources. Some adapt to shade, thriving beneath larger plants. Others specialize in disturbed areas where floods or storms clear land. These different strategies create layers within forests. A canopy forms overhead. Smaller trees form a middle layer. Shrubs and early flowering plants develop beneath. Mosses and ferns carpet the forest floor. Layers support different kinds of organisms, forming complex interactions. As forests mature, their influence on climate becomes profound. The increased oxygen production continues shifting atmospheric composition. Forests store vast amounts of carbon in their trunks, roots, and soils. This storage reduces carbon dioxide in the atmosphere, cooling global temperatures in some regions. Forests also influence rainfall. Trees release water vapor through transpiration. This vapor forms clouds, promoting more rainfall in forested areas. Forests become self-sustaining climate engines. Their spread changes wind, temperature, and moisture patterns across continents. Over time, forests adapt to unforeseen challenges. Droughts, volcanic eruptions, and shifting continents reshape them. In some regions, fires begin playing a natural role in forest cycles. Plants evolve fire-resistant bark, seeds that germinate after heat exposure, or the ability to regrow quickly after damage. Other regions remain moist enough that fires rarely occur. Each adaptation creates a distinct forest type. Tropical forests arise near the equator, where rainfall is abundant and temperatures warm. Temperate forests emerge in moderate climates with seasonal changes. Boreal forests form in colder regions. Each forest type relies on the basic principles of early plant evolution, but carries its own unique features shaped by local conditions. The catastrophe that wiped the world clean no longer defines these forests. They are shaped instead by the conditions that developed afterward: weather, water, soil, and the slow work of evolution. They're emergent signals that the planet has regained enough stability to support long-term biological structures. They are not simply collections of trees. They are systems that influence the entire planet. They create habitats for countless organisms. They moderate temperature. They store elements that influence the atmosphere. They carve new boundaries for rivers and shape the chemistry of the soil. By the time forests have truly established themselves, life on land has diversified beyond simple plants. Insects or insect-like creatures evolve to pollinate certain species. Small animals, primitive at first, establish niches within the forest layers. Fungi spread through the soil, connecting trees through underground networks and recycling nutrients from dead wood. These interactions strengthen forest ecosystems further. Life no longer exists in isolated pockets. It forms interconnected webs where each part influences the others. Forests do not just return, they redefine the world. They create microclimates within their canopies. They alter wind patterns around their edges. They sculpt entire continents by preventing erosion and promoting soil formation. The landscape becomes structured not by empty rock and sediment, but by the geometry of branching limbs and spreading roots. Every valley, ridge and basin acquires new meaning once forests anchor themselves to the ground. When forests try for a second time, they build a world capable of supporting complexity far beyond what came before. They lay the foundation for future creatures, large, small, swift, slow, to find places to feed, breathe, shelter, and thrive. The quiet landscapes that once held nothing but rock and the remnants of catastrophe become networks of life, woven from tiny innovations that began in tidal pools and shadows. Their return marks a turning point, where the planet moves from rebuilding itself to becoming a place where life can flourish again, in forms that will continue rising in complexity long after the first forests have taken root. Humanity's presence in a remade world would not begin with confidence. It would not begin with certainty, direction, or the sense of mastery that earlier civilizations once believed they possessed. Instead, it would begin with a kind of unfamiliar quiet, a space shaped by forests that grew without human influence, oceans that rebuilt their ecosystems through cycles far older than memory, and skies that regained their clarity without any of the technology or industry that once filled them with haze. In such a world, humanity, whether re-emerging from scattered survivors or arising far later as a new evolutionary branch, would have to rediscover its place slowly, humbly, and with far more awareness of how small any species truly is in the face of planetary time. Before humanity can find its place, the conditions that support humans have to exist. Breathable air must already be present, stable enough to maintain oxygen levels across continents. Forests must have returned, shaping climate and anchoring soil. Rivers must run predictably, providing freshwater networks that spread across valleys and plains. Oceans must be full of life, distributing nutrients and maintaining weather cycles. The planet must once again be a world where ecosystems generate excess energy that can support animals, not just plants and microorganisms. Only then can a creature as metabolically demanding as a human exist. If humanity survived the catastrophe in small numbers, their early generations would encounter a world that feels simultaneously familiar and alien. Familiar in that the basic requirements for life, light, water, warmth, food, still exist. Alien in that everything else has shifted into new forms. The forests that stand across the land would not resemble the forests of the old world. The animals, early descendants of the species that reawakened during the renewal period, would behave differently from those once documented by science. The climate patterns might follow cycles that feel unfamiliar. Even the constellations in the night sky could be altered by tiny shifts in Earth's rotation or axial tilt. In such a world, humanity's role would start from reliance rather than dominance. Early humans would focus on survival, finding food sources, learning the habits of new animals, and discovering which plants are safe to consume. They would have to pay attention to the rhythms of their surroundings because the environment, shaped by millions of years of natural recovery, would not bend easily to human needs. The land would not have the scars of roads or the edges of cleared fields. Everything would be raw and natural. Humanity would have to approach it with patience. Generations born into this world would grow up without memories of the pre-catastrophe era. Their myths, stories, and cultural foundations would develop around the landscapes they inhabit. Rivers would become their landmarks. Forests would become their shelters, challenges, and sacred spaces. Mountains would become symbols of permanence. The sky, clearer than any human of the previous age ever witnessed, would influence their understanding of time, direction, and seasons. Their sense of belonging would develop in relation to the planet itself. not in relation to technology or global infrastructure. If humanity did not survive the catastrophe and instead re-evolved from earlier primate lineages after millions or tens of millions of years, their arrival would follow a different path. Whatever descended from these ancestors would emerge into a world already filled with established forests, complex food webs, and balanced global systems. The planet would not shape itself around humans. Humans would have to shape themselves around the planet. In this scenario, the traits that lead to human-like cognition would develop because they serve practical purposes in the new world, navigating forests, communicating within groups, solving problems related to food gathering, or interpreting complex social dynamics. In either case, survival or re-evolution, humanity's place in the remade world would depend heavily on the choices made by early societies. If early humans attempted to recreate the technological structures of the past, without understanding the fragile balance of the new ecosystems, they would face immediate consequences. Forests that regulate rainfall could collapse if overharvested. Rivers could shift unpredictably if disrupted. Animals on which humans depend could vanish if hunted beyond sustainable levels. A remade world, fresh from the long recovery after catastrophe, would not tolerate rapid exploitation. The planet would respond with instability, as it did countless times in its deep history when environments were overburdened by sudden pressures. For this reason, humanity's long-term survival in a remade world would likely be tied to their ability to work with natural systems rather than against them. Early communities would need to observe cycles, understand seasons, learn migration patterns, recognize the importance of water sources, and avoid disrupting critical habitats. These skills would not be optional. They would be the basis of longevity. Cultures that learned to coexist with their environment would thrive. Cultures that attempted to dominate it too quickly would face scarcity and collapse. Agriculture, if it reappeared, would emerge slowly. The new plants of the world might not immediately lend themselves to domestication. Their reproductive cycles, nutrient requirements, and responses to human manipulation would differ from the crops that once supported human civilization. Early humans would need to experiment with local species, gradually selecting the ones that respond well to cultivation. This process could take centuries. During that time, humans would rely heavily on foraging, hunting, and the careful observation of the landscapes around them. Animals, too, would present new challenges. The creatures that re-evolved or repopulated the Earth after the catastrophe would not behave like familiar species. Some might be cautious, others bold. Some might form herding behaviours that allow domestication. Others might remain solitary and difficult to approach. Predatory species could develop in ways that humans would need to contend with, shaping how communities build shelters, defend themselves, and move across the land. Understanding these animals would require patience, adaptability, and a willingness to learn from failure. Technology in this remade world would develop within the constraints set by the planet's new conditions. Metallurgy might begin later if accessible ore deposits were reshaped or buried by the catastrophe. Early tools might rely heavily on stone, wood, and bone. Fire-making techniques would depend on the types of plants and resins available. Craftsmanship, pottery, weaving, shelter building would evolve in response to local resources rather than inherited knowledge. Communities would have to rediscover fire-resistant woods, strong fibres, and durable clays by experimentation. As generations pass, humanity's relationship with the remade world could follow several paths. One possibility is that societies develop in harmony with their environment, creating cultural traditions that emphasize balance, sustainability, and respect for natural cycles. Such societies might treat forests as spaces of deep importance, rivers as sacred, and wildlife as partners in survival. Their myths could be built around the memory of the world's recovery, even if they do not know the details of the catastrophe that came before them. They might view themselves not as rulers of nature, but as participants in a vast, complex system that they must understand to survive. Another possibility is that humanity eventually rediscovers advanced technology, but this time with an awareness of the fragility of planetary systems. If knowledge of the pre-catastrophe era survives in oral stories, symbols, or scattered remnants of old infrastructure, these fragments might guide future societies. They could inspire caution, warnings passed down about a world that once existed and then vanished due to imbalance. Technology reintroduced under these conditions might develop differently. Cleaner energy sources could emerge first. Resource-intensive practices might be avoided altogether. Societies might build in ways that respect ecosystems rather than override them. Yet another possibility is that humanity's place in the remade world becomes one of coexistence with other species that evolved alongside them. Larger animals might re-inhabit regions that humans later settle. Some would become competitors for food or territory. Others might become allies in mutual survival. The evolutionary pressures of a new world could produce animals with intelligence different from but potentially comparable to that of early humans. Humanity would not exist alone at the top of an ecological pyramid. They would share the world with other complex creatures, each shaped by the same cycles of recovery and adaptation. Regardless of the path taken, humanity would find itself in a world where survival depends on understanding systems much larger than themselves. Weather patterns shaped by forests and oceans would dictate growing seasons. River cycles would determine settlement patterns. Soil richness, influenced by millions of years of biological rebuilding, would define agricultural potential. Humanity's role would not be predetermined by its past. It would be shaped entirely by this new set of relationships. Culturally, societies might become deeply observant. Without immediate global communication, knowledge would spread slowly through generations. People would read signs in the landscape, notice subtle changes in weather, track the behavior of migrating animals, and adjust their strategies accordingly. This intimate connection with the environment would become part of daily life. Songs, rituals, and storytelling could center on the seasons, the growth of forests, and the cycles of the moon. Human identity would intertwine with the rhythms of the planet. As human populations grow, interactions between groups would influence how they see themselves within the remade world. Some communities might remain nomadic, following herds or seasonal resources. Others might establish permanent settlements along river valleys or within fertile forest clearings. Conflicts could arise when resources overlap, but alliances could also form through trade, cooperation, and shared ecological knowledge. The relationships between human groups would reflect the landscapes they inhabit. In time, humanity might reach a moment where it recognizes the planet not as a resource to be drained, but as a partner in continuity. This recognition could form the basis of long-term stability. A culture built on the understanding that forests took millions of years to return would treat them differently. A culture aware that oceans rebuilt their ecosystems through delicate cycles would avoid disrupting them. A culture conscious of air that once nearly disappeared would respect its fragility. These values would shape large-scale decisions, guiding humanity toward practices that prevent another collapse. If the species manages to maintain this balance, its place in the remade world becomes not one of dominance, but of integration. Humanity becomes a thread woven into the planet's fabric, influencing it, but never overshadowing it. They take part in maintaining the cycles that sustain life rather than unraveling them. And if, someday, humans once again build cities, carve paths across continents, or reach for scientific understanding, they do so with the memory of a world that once had to rebuild itself from nothing. Such memory, whether preserved through stories or instinctively carried through culture, becomes a quiet force shaping how humanity moves forward. It does not erase ambition or creativity, it simply provides context. In that context, humanity's place in a remade world is neither predetermined nor fixed. It is something discovered slowly, shaped by patience, awareness, humility, and adaptation. A place earned through understanding rather than assumed through birth. a place where survival is tied not to the ability to change the planet, but to the ability to live alongside it. In a world rebuilt over millions of years, a world where forests learned to grow again, oceans reshaped their ecosystems, and life restarted from its smallest possibilities, the rules that once governed survival no longer apply in the same ways. Old assumptions fade, old patterns dissolve. What worked for the species of the pre-catastrophe Earth does not automatically work for those living in this restored version. Everything has shifted. Climates, landscapes, food webs, seasons, balances of resources, dangers, rhythms. The planet has become a new system, shaped not by memory, but by the long geological patience that carried it from desolation to renewal. And within this new system, the principles that govern existence must adapt. The first rule emerges from the planet itself. Survival depends on stability, not dominance. In the old world, humans and other species often acted as if overcoming or controlling the environment led to security. But in a newly rebuilt Earth, ecosystems are still young. Forests are only beginning to reach maturity. Soil networks are developing. Rivers are settling into their long-term paths. The balances that sustain life are delicate. Any species that tries to push against these balances too aggressively risks immediate consequences. Competition still exists. Life has always relied on it. But the competition now occurs within tight boundaries. Those who survive are the ones who recognize limits early and learn to work within them. From the smallest microorganisms to the first complex animals of the renewed world, adaptation becomes more important than strength. The environments created during planetary recovery are dynamic but predictable in their cycles. Organisms that can adjust their behavior, metabolism, or migration patterns in response to shifting resources thrive. Those that remain fixed in their habits risk disappearance. For early species re-establishing themselves in forests and oceans, flexibility becomes the trait that determines which lineages expand and which fade. This rule applies equally to any intelligent species that emerges. Predictability comes only from learning the rhythms of the land, sea, and sky. Another rule grows from the interconnectedness of recovering ecosystems. Survival and harmony rely on awareness. This awareness is not philosophical, it is practical. Species that sense environmental changes early, temperature shifts, resource fluctuations, chemical changes in the water, gain advantages. In forests, animals develop acute senses to read subtle patterns in vegetation or soil moisture. In the oceans, schooling species respond instantly to pressure changes or the behaviours of predators. On land, emerging species learn the signs of seasonal variation or the habits of others. Awareness becomes one of the most powerful survival traits. Humans or human-like beings entering this remade world must adopt the same trait. Those who pay attention to nature's patterns have an easier time finding food, building shelters, predicting storms and avoiding predators. Those who ignore these signals risk losing their footing in an environment that no longer bends to human needs. In this sense, harmony is not idealistic, it is necessary. The land rewards those who listen. As ecosystems evolve, another principle takes hold. Cooperation often outperforms competition. In the early stages of life's return, cooperation emerges naturally in microbial communities, plant networks, and simple animal groups. The organisms that form alliances, exchanging nutrients, sharing protective behaviours, or specialised roles, become more resilient in the face of environmental shifts. Underground networks of fungi help forests distribute resources. Mixed species herds develop safety strategies. Predator-prey relationships stabilise in ways that prevent ecosystem collapse. Cooperation reduces chaos, allowing ecosystems to establish cycles that life depends on. For humans, cooperation extends beyond forming communities. It becomes essential for long-term survival. Working with other species may influence everything from early agriculture to resource management. Watching how forests self-regulate teaches communities how to avoid overharvesting. Observing predator behavior teaches defensive strategies that reduce conflict. Harmony becomes a survival tactic rather than a moral choice. Over time, the reborn planet shapes another rule. Energy efficiency becomes the foundation of all thriving systems. Life, whether primitive or advanced, cannot waste energy in a new world where resources build slowly. Every species that emerges after a catastrophe inherits tight energy budgets. Plants optimize photosynthesis. Herbivores develop digestive systems suited to new vegetation. Predators refine their hunting strategies. This efficiency builds ecological stability. Species that use resources recklessly burden themselves and weaken their chances of surviving environmental stress. If human communities reappear, they face a similar reality. Tools, shelters, and social systems must be energy conscious. Inefficient behaviours, whether in hunting, gathering, or building, threaten survival. Harmony with the natural system again becomes a practical necessity, guiding societies to conserve rather than exploit. Waste becomes a danger. Sustainability becomes instinctive. Another rule emerges gradually as ecosystems diversify. Mobility is a form of resilience. Species able to relocate efficiently, whether across forest canopies, through mountain valleys, or along coastlines, manage environmental changes better than those confined to narrow habitats. Seasonal variations, weather patterns, and resource cycles push organisms to remain mobile. Even plants evolve mechanisms for seed dispersal that extend their range. Wind-dispersed seeds, waterborne seeds, or fruit strategies that rely on animals. Humans in the remade world also find value in mobility. Early communities may need to shift with herds, with seasons, or with plant cycles. Settlements that remain fixed in areas prone to flooding, drought, or soil depletion struggle. Societies that build flexibility into their movement patterns thrive. Harmony extends not only to behaviour but to geography, knowing when to stay and when to go. As forests expand and animal life diversifies, another rule becomes unavoidable. Risk is distributed unevenly, but resilience grows where risk is understood. Early predators emerging in the restored world shape migration patterns, herd structures, and behavioural instincts. Prey species develop strategies not through brute strength, but through awareness, speed, and group behaviour. This interplay produces balanced ecosystems where no single species dominates fully. The world has learned from its collapse. It does not allow dominance to go unchecked. In this context, humans are no exception. They must understand risks, predators, resource fluctuations, natural disasters, and respond strategically. Harmony here means respecting boundaries, avoiding certain territories during specific seasons, letting rivers flood natural basins, allowing forests to burn in cycles that clear underbrush. These actions are not guided by philosophy or environmental ethics. They are built into the survival strategy of species living in a system that rebuilt itself slowly and carefully. One of the most significant new principles reveals itself through the behaviour of forests. Growth depends on cycles, not continuous expansion. In the old world, humans often sought constant growth. Larger populations, broader territories, increased consumption. But every ecosystem in the remade world follows cycles: birth, death, renewal, rest, resurgence. Forests grow and shed, rivers rise and shrink, oceans fluctuate in nutrients and temperature, animals breed seasonally, plants fruit only during optimal conditions. Every part of the world moves according to patterns that require pauses. Species that push beyond these cycles strain their ecosystems and suffer the consequences. Those that synchronize with natural rhythms become stable parts of the landscape. This lesson applies directly to any intelligent species. Communities that grow too rapidly find their resources depleted. Those that pace themselves, expanding only when ecosystems can support expansion, achieve long-term presence. Another rule develops as ecosystems mature. Diversity strengthens survival. The catastrophe that preceded this new world likely eliminated countless species, leaving narrow pockets of survivors. As life reawakens, those pockets diversify. The more variation in a forest, the more resistant it becomes to disease or climate shifts. The more variation among animals, the better they handle predators, weather extremes, and resource fluctuations. Diversity becomes the planet's buffer against instability. For human or human-like beings, diversity in skill, knowledge, and cultural practices becomes equally crucial. Communities that rely on a single food source, a single construction method, or a single migratory pattern become vulnerable to disruption. Communities that cultivate a wide range of practices, foods, and tools remain resilient. Harmony emerges not from sameness, but from variation that allows adaptation under uncertain conditions. As ecosystems reach balance, a rule surfaces that defines long-term stability. Balance arises from limits, and limits are essential to harmony. No species grows indefinitely. No forest expands without boundaries. No ocean system maintains infinite productivity. In the old world, humans often viewed limits as obstacles. In a remade world, limits become guides. They show species how much they can take, how much they can grow, and how much they must give back to maintain equilibrium. Those who follow these limits survive, those who ignore them collapse. In this environment, the relationship between species becomes part of the rule set. Interactions define success. Predator-prey dynamics keep populations in check. Pollinators, whether insects, birds, or emerging equivalents, support plant reproduction. Scavengers recycle nutrients. Microbes decompose waste. No organism acts alone. Harmony is not a peaceful utopia. It is a continuous negotiation where every participant plays a role. Understanding these roles becomes critical for any species wishing to live sustainably. As human or human-like societies develop, they encounter the final, overarching rule. Knowledge becomes the axis of harmony. The more a species knows about its environment, its cycles, its dangers, its rhythms, the more effectively it can survive within it. Knowledge here is not abstract. It is observational and practical. When to plant, when to migrate, how to store food, how to manage fire, where predators hunt, how rivers behave, how forests recover after storms. Cultures that embed this knowledge in their traditions, stories, and collective memory achieve stability. Those that forget or ignore it risk losing the delicate harmony the planet rebuilt. Over thousands of years, these rules shape the behavior of every species living on the remade Earth. They create a world where survival and harmony are deeply intertwined, not because life has become gentle or simple, but because the planet's recovery demands it. The catastrophe that once erased the old world taught the new one how fragile complexity can be. The ecosystems that re-emerge carry those lessons forward, enforcing balance through natural constraints, rewarding adaptation and cooperation, and ensuring that no single species can destabilize the cycles that sustain life. In such a world, harmony is not a philosophy. It is the natural consequence of countless interactions, each one contributing to the stability of the whole. And survival is no longer a matter of domination or excess. It becomes a quiet partnership between species and environment, shaped by cycles, limits, awareness, and the long patience of a planet that rebuilt itself from the edge of nothing. A future that grows out of a remade world does not take shape in sudden leaps. It does not arrive with clear boundaries, obvious milestones, or grand turning points that announce themselves to the species living through them. Instead, it unfolds in subtle layers, shaped by the slow accumulation of choices, adaptations, and interactions. Everything that happens in this new era begins with the foundations the planet rebuilt. forests that learned to grow again, oceans that selected their creatures through cycles of pressure and opportunity, atmospheres that discovered balance through chemical patience, and landscapes that recorded the memory of renewal in every ridge and valley. A future gently reimagined arises from these quiet transformations, carrying forward the lessons embedded in the planet's recovery. The earliest generations living in this new world experience a life defined by simplicity, by close attention to their surroundings, and by the rhythms that shape the land. Whether they are descendants of survivors or entirely new beings evolved long after the catastrophe, their future is influenced by the environmental constraints around them. They live according to seasons rather than clocks, landscapes rather than borders, and relationships with other species rather than systems of extraction. Their needs are straightforward: food, water, safety, connection. Their means of achieving these needs develop slowly, guided less by ambition and more by careful observation. With each passing generation, knowledge becomes more structured. Early societies learn to read the land not just as a resource, but as a partner in survival. They notice how certain plants respond to rainfall patterns. They observe how rivers behave during cycles of drought and abundance. They record the habits of animals, not through written language at first, but through memory and shared stories. These stories shape early culture, giving meaning to natural events that once felt mysterious. The future at this stage is defined by how well the species understands the world around them. Slowly, tools evolve, not as remnants of a lost civilization, but as new inventions guided by the materials available in the remade world. Stone shapes become sharper as techniques improve. Fibers from new plants are woven into ropes, nets, and simple garments. Clay becomes the basis of pottery that stores water or protects seeds. Fire becomes easier to harness as communities learn which woods burn cleanly and which produce smoke or sparks that threaten the forest floor. Each advancement builds on the last in steady increments. The future takes shape one practical improvement at a time. As communities grow larger, the landscapes they inhabit begin shaping their identities. Those who settle near rivers become adept at managing seasonal floods, building platforms or structures that rise with the water. Those who live in dense forests learn to navigate canopy light patterns, using clearings for food cultivation and shaded areas for shelter. Those who dwell near coastlines develop knowledge of tides, currents, and the behaviour of ocean life. These geographical differences lead to distinct cultures, each one adapting to its surroundings in ways that make sense only within that particular environment. A gently reimagined future is not uniform. It branches across the planet just as ecosystems do. In some places, communities choose to remain nomadic, following migrations of animals through forest corridors or across open plains. In others, settled villages emerge, built around reliable water sources or sheltered basins where storms are less severe. Over time, these villages develop into small networks of exchange. Trade arises naturally, not from a desire for wealth, but from practicality. One region might have access to certain minerals, another to fibres, another to medicinal plants. As these exchanges become common, relationships between communities strengthen. Language evolves alongside these exchanges. Patterns of sound, gesture, and symbol begin to represent common ideas: the cycle of seasons, the migration of animals, the safety offered by certain landmarks. As language develops, storytelling shifts from simple memory preservation to reflections on meaning. Myths arise, not as literal records of the past, but as frameworks for understanding the world. These myths often centre on the planet's renewal, the return of forests, the reawakening of oceans, the slow rise of breathable air. They do not describe the catastrophe itself in scientific terms, but express the awareness that the world was once empty and is now full. Through these stories, a sense of humility takes root. The beings living in this new world, whether human or human-like, sense that the Earth is something that rebuilt itself through long patience, not through intervention. This understanding shapes cultural values. Respect for natural cycles becomes instinctive. Overharvesting becomes taboo. Wastefulness becomes rare. Traditions develop around maintaining balance, treating forests as living partners, rivers as sources of renewal, and animal species as fellow participants in the shared web of existence. The future at this stage begins to resemble something stable, something capable of lasting far beyond the memory of the early generations. Agriculture appears gradually, not in the sweeping transformations seen in earlier human history, but in careful experimentation. Communities identify plants that respond well to human cultivation, species that thrive when given space, water, and protection from competing vegetation. They select seeds that grow more reliably, more nutritiously, or more predictably. Over centuries, domestication takes place. What were once wild, unpredictable species become staples of daily life. As agricultural knowledge spreads, communities gain more control over food supply. This does not immediately lead to large populations or urban centres. Instead, it makes life more secure. Fewer individuals need to spend their days searching for food. More time becomes available for craftsmanship, teaching, exploration, and reflection. Tools grow more sophisticated. Settlements grow sturdier. Social structures become more organised. The future begins to resemble a world where stability allows creativity. As societies develop, so does their relationship with other species. Some animals become companions, creatures that sense human intentions, respond to training, and contribute to daily tasks. Others become guardians of forests or indicators of environmental change. In this remade world, species interactions carry profound consequences. A decline in one population can trigger shifts across entire systems. Because early societies observe these patterns so closely, they incorporate respect for biodiversity into their cultural practices. Their future decisions are shaped by the awareness that every species plays a role in the stability of the whole. The planet itself continues to evolve alongside its inhabitants. Forests reach new levels of complexity with layered canopies, diverse underbrush, and intricate soil networks. Oceans stabilize into vast ecosystems that support everything from microscopic organisms to sophisticated predators. Rivers mature into predictable waterways that carve valleys and nurture fertile plains. Weather patterns settle into recognizable cycles. The climate becomes a partner in daily life rather than an unpredictable force. With this environmental maturity, the future becomes more expansive. Exploration becomes possible. Communities begin travelling farther, across mountain passes, through forest corridors, along river deltas. They map the world informally through memory and tradition. They discover regions with different ecosystems, climates, and resources. These discoveries influence cultural evolution. Some communities integrate new knowledge to improve their survival strategies. Others merge practices with groups they encounter. In this way, the future becomes shaped by both movement and merging, a slow weaving of experiences into collective growth. With time, symbolic thinking deepens. Art emerges from pigments found in clay and plants. Patterns carved into wood reflect the shapes of leaves or water currents. Music arises from wind instruments, drums crafted from animal hides, and stringed tools made from plant fibers. Cultural expression becomes a way of connecting individuals to each other and to the planet. The future becomes more than survival. It becomes meaning. Technology continues evolving in ways that remain grounded in environmental balance. Fire becomes controlled and deliberate. Early metallurgy appears when communities learn to extract metals from exposed deposits left behind by the catastrophe. Pottery grows more sophisticated. Structures become more durable, incorporating designs that respond to wind, rain, and seasonal variations. Navigation improves with the use of stars, landmarks, and environmental cues. Each advancement remains shaped by a respect for limits. The world teaches caution through previous cycles of collapse, even if the details of that distant catastrophe have long since faded into myth. As societies become more established, they face new questions. How should they manage resources when populations grow? How should they respond to conflicts over territory? How should they share knowledge across distances? These questions shape new social structures, councils, gatherings, agreements between groups. Solutions reflect the core principles that have defined life in a reimagined world: balance, awareness, cooperation, and adaptation. The future at this point begins to carry a quiet wisdom. It recognizes that long-term stability depends on cycles rather than continual expansion. It values diversity as a safeguard against uncertainty. It views landscapes as living systems rather than empty spaces. It treats knowledge as a communal resource rather than a private possession. The planet becomes a partner rather than a backdrop. Over generations, this future deepens. New inventions emerge that harness energy more efficiently. New forms of communication connect distant communities. Trade networks grow. Societies become increasingly able to adapt to environmental changes, droughts, storms, migrations, without undermining ecosystems. The world feels alive, not just biologically, but culturally. It breathes through the actions of its inhabitants. Eventually, if an advanced civilization rises in this remade world, its foundations differ from the ones that came before. It does not grow from an unchecked pursuit of power or expansion. It grows from the patient layering of knowledge, the careful management of resources, and the cultural emphasis on harmony that shaped every generation before. Energy sources are chosen for their sustainability. Settlements are designed to blend with ecosystems rather than overwhelm them. Scientific understanding coexists with deep respect for natural limits. A future gently reimagined becomes a future where the boundaries between nature and civilization blur. The world is no longer a stage on which life acts, it is an active participant. The species that inhabit it understand that their survival depends on maintaining the cycles that rebuilt the Earth. This understanding becomes a guiding principle for every major decision, from how to cultivate land to how to build shelters to how to structure communities. Such a future does not eliminate difficulty. Storms still come, diseases still arise, resources still fluctuate, but the societies living in this world approach challenges with resilience built from generations of listening, observing, and adapting. They see change as part of the natural rhythm rather than a threat. They face uncertainty with the knowledge that life has rebuilt itself before and can do so again, as long as balance is preserved. In the end, a future gently reimagined is not defined by grand achievements or towering monuments. It is defined by continuity, by the quiet confidence that life, in all its forms, has found a way to coexist with the planet that sustained it. It is a future shaped by humility, infused with awareness, and strengthened by the memory of a world that once had to rebuild itself from the edge of nothing.